Hi everyone. Just Hi everyone. Just let me know if you can hear me. So good morning everyone. I'm Sachin. How are you doing? How's your preparation going on? Okay. So today we are going to discuss transport layer as I said yesterday also. So today we were planning first like algorithms, but then some people were saying that they need transport layer to be discussed. So that's why we will be discussing the transport layer. Okay. So let's just get started. And in the transport layer, we will be discussing everything that is required for gate syllabus and computer networks. Okay. So let's get started. And in the transport layer, we are going to see TCP and UDP. So we will be starting with UDP first, right? Cool. Let me know if you have any doubt from earlier lectures, and then if you do not have any doubt, then we can start. So hello Vishnu, good morning. So let's just get started. Now in the transport layer, as I said, like we are going to discuss TCP and UDP, and first we will be discussing the UDP. So let me start with this diagram. This diagram is representing that how transport layer works and what is the need of transport layer. Okay. So in the transport layer, we say that we are going to communicate host from this port to port. So there is a host and this is server or some host, and you want to communicate from this host to the server or vice versa. So what you need to do, you need to communicate till the socket. Socket means you need to communicate till port to port. So transport layer is responsible for communicating port to port, right? So which means, let's suppose that you have some source host number, you have some destination port number, and you have these two port numbers, and using these two port numbers you want to communicate, right? So what you will be doing, you will be saying that you can communicate using the transport layer. If you want to communicate between two hosts, then you have to use the transport layer because that is responsible for port to port communication. So let's see that how it works. Now there are various protocols at the transport layer. First is UDP and second one is TCP, which are in our syllabus. So UDP is very simple and connectionless, unreliable transport layer protocol. So now you might be wondering that why we need anything which is unreliable and what do we mean by connectionless first of all. So I will answer both of the question, that what do we mean by connectionless and why we even need the unreliable protocols. But before that, let me just give you the overall architecture of this UDP and then you will get to understand. So basically it does not add anything to the services of IP except for providing process to process or host to host communication, and this is very light protocol. Light in the sense that you do not need to do much things here, you just need to get started, and then you will say that for this protocol you do not need any much jargons, like it is very simple protocol. Okay. So let me just tell you that what is the packet or what is the header of UDP and how does it look like. So as you can see here, this header is extremely simple. You just have source port number, destination port number, what is the total length, and what is the checksum. That's all. Like you do not have anything else. You just have these four fields. Now let's just check. Let's just see that how does the checksum get calculated. Okay. So let's just see that how does this checksum get calculated, and given some header how to find out all of these numbers. So for example, let's suppose that header in the UDP is given like this. So I have taken these questions mostly from everything that I'm going to teach is taken from the Frozen. Okay. Siddhi is asking, sir, yesterday, as you said, lecture, this LSR sum is expected. Then can you please take one example? This year LSR sum is expected. Okay. I mean, see, no one, it's not like that no one can, no, like someone can tell you that what is expected in GATE. So it is just like I was just saying that maybe they can ask LSR. It doesn't mean that they will be asking LSR. So don't worry, we will be covering those questions in the All India mock test or in the mock tests there. So it's not like that I'm saying that it is expected, then there will be a question. So I mean, I just said like they have asked a DVR a few times and LSR just I think one time. So they may ask LSR. That's the only reason that I'm giving, right? I cannot predict that what is going to they ask in the GATE examination. So I mean in LSR actually the things are very simple. Maybe there is no question behind the LSR that they can ask. That's why they are not asking, right? Okay. So suppose that this is the UDP header that is given to you, and they ask you what is the source port number. Then how do you calculate the source port number? You see the header. This is the 16 bits initially is basically telling you the source port number. 16 bits means 2 bytes. So here here these are the 2 bytes. So you can say the source port number is CB84, right? That's very easy. You can say CB84 in the hexadecimal is your source port number. So using the header, you can tell the what is the source port number, which is very easy. Okay. And then if they ask you that what is the destination port number, then you will say the destination port number is next 16 bits. So which means that this is destination port number, right? So the source port number and destination port number are initial 16 bits or 2 bytes. So this is source port number, and then this is what the destination port number is, right? So this is destination port number. And then what they're asking, what is the total length of the user datagram, and what is the total length? It is again, if you see next 16 bits or maybe 2 bytes. So this is the total length, right? And then they ask you what is the yeah, this is interesting, what is the length of the data. So as you know that the total length minus the header length will be the length of the data. So if this is the total length, which is coming out to be, like, if you convert that to decimal, then it is coming out to be 28 bytes, right? So you can convert that to decimal. How? This is 1C. C means this is A, B, C. C means 10, 11, 12. So this is C. 1C will be 1C in hexadecimal will be 16 power 0 into C. C means 12 plus 16 power 1 into 1, right? Which is 16 plus 12, which is 28. And this total length is represented in bytes. So basically this is 28 bytes. And this is total length including the header, right? Now if they subtract the header, which is of 8 bytes only, then you will be getting the data length, right? That's how you can get the data length. Now they're asking what is the length of the data. So you can subtract this 8 bytes, and then you can get the length of the data. Is the packet forwarded from client to server or vice versa? So yeah, that's very nice question. So they are asking this is very standard question that I have taken from Trojan. So they are asking whether the packet they are forwarding is from client to server or vice versa. So see here, the source port number and the destination port number, right? Source port number and destination port number are the initial. So if you convert that to decimal and that to decimal, then you will be getting, if you convert this to decimal, then you will be getting 52100. So basically the source port number here is 52100, and the destination port number here is this one 000D. D means A, B, C, D, right? So A, B, C, D. So this is 10, 11, 12, 13. So which means the destination port number is 13. So now tell me, if the source port number is 52100 and destination port number is 13, then can you tell me that whether it is going from source, I mean client to server or server to client? What do you think? The destination is 13, which is not a general purpose port, right? I mean, source is taking some general purpose port, some generic port, and destination is taking some specific port. So 13 is a well-known port, and that's why this is for the server. Okay. 13 is for the server. So basically you will say that 13 is a well-known port, that's why you are going from client to server. So you will be saying that the packet is going from client to server. Client to server. Okay, cool. Now the third field here is third or fourth field here is checksum. So let me just tell you that how do you calculate the checksum. It is also very easy to calculate the checksum. Let me just show you how. So I have taken the example of IP before, where also you have one field which is checksum. So using this example, you will get to understand how does the checksum get calculated, and then I will ask you some question related to it. Okay. So how to calculate the checksum? If you want to calculate the checksum, then what you need to do, you see what are the number of bytes in the checksum. So suppose here the number of bytes are 16 bits, which means 2 bytes, right? Suppose this is 16 bits. This is again the 16 bits, right? This is IPv4 header basically. Okay, the example that I'm taking is for IPv4 header. So initially you have header length and then so on, right? So there is a particular structure of IPv4 header. Now what I'm asking you that how to calculate the checksum. What you will do, you will put all the zeros here in the checksum, and then you will, if this is of 16 bits, you will group each 16 bits. You will take 450, right? This 16 bit, and then this 16 bit, you will group each 16 bits. So this is one group, this is another group, this is another group, this is another group, like that. You will group each 16 bits, and then you will arrange them vertically, right? So this is IP address, this IP address. So you will divide that into two parts because it is 32-bit IP address. So you will group each 16 bit. You will, because the checksum is of 16 bit, and then you just simply do the sum. Okay, you simply do the sum, and then you say, yeah, then you say that this like whatever sum you are getting, then if you are getting any carry, then you have to wrap around that carry, which means you need to add this carry again to the sum, and then finally you are getting this, and then you will say that this is your checksum. I mean, then you take one's complement of it, and then you say this is your checksum. That's how you calculate the checksum, right? So I hope you understood. Let me just tell you how to calculate the checksum for the UDP. Then maybe you will understand this more clearly, right? So suppose that this is the UDP header, and you want to calculate the checksum. Okay, you want to calculate the checksum for the UDP header. Then let's just do it quickly for one of the example. Okay, and suppose that header is given to you is this one. Okay, then sorry. Let me copy it. Okay, so suppose this is the header that is given to us, and then they are asking that how to calculate the checksum. So how to calculate the checksum? What you will be doing? You will be basically dividing this header into this. This is 16 bits, so you will be dividing this header to 16 bits, right? So you will say that let me divide this header into 16 bits. So this is first 16 bits, then this is next 16 bits, right? So whatever was the header, you will divide that header into 16 bits. Then this is next 16 bits, right? And then this is next 16 bits. And for the last 16 bits, since you do not know the checksum, you just keep it zeros. Okay, you just keep it zeros. Initially, you just keep it zeros. Suppose you do not know the checksum initially, obviously because we want to calculate it. Now what you do? You convert that to binary. You convert that to binary. You convert that to binary, and then you add all of it. Okay. So you can convert each of this number in the hexadecimal and binary very easily, because each of this number you can convert individually. For example, if you want to convert this into binary, so 4 will be 0 1 0 0, right? This is 4. 8 will be 1 0 0 0. B will be, B means 11. 11 means 8 plus 2 plus 1. 8 2 1. And then this is C, which is 12. 12 means 8 plus 4. So basically this is how you can convert this to binary. Similarly, you can convert this to binary. So D means 13. D means 13, which means 1 1 0 1, and then everything else is 0. Right. Now the C means 1 1 1 0 0, 0 0 0 1, and then everything else is 0. Right. And now this is already 0, so don't worry about it. And then you need to add all of it. If you add all of this, this will be 1, this will be 0, this will be 1, and carry will be 1, this will be 1, then carry will be 1, this will be 0, then carry will be 1, then this is 1, this is 0, and then this is again 1, this is 1 1 0 1, it is as it is, right? 1 1 0 0. So now you have not got any carry, that is fine. So this is your checks, this is the sum that you have got, and now you take the ones complement of it, and then you get your checksum. I hope now you understood that how to calculate the checksum. Now let's just see. Yeah, so basically this is how we calculate the checksum. Now let's just see that what kind of errors this checksum can detect and what kind of errors this checksum will not be able to detect. Okay, so what do you think? Let's suppose this is how we are calculating the checksum. What do you think? What kind of errors it will be able to detect? See, if let's suppose, see, I need this sum, right? Now let's suppose if you are having something where let me give you example here. Let's suppose this is 1, this is 0. Suppose this 0 and 1 get flipped, which means these two bits get flipped, which means this 0 get converted to 1 and 1 get converted to 0. Then will the checksum will ever be able to detect that there is an error? No, right? Because checksum is dependent on sum. As long as each column is having the same sum, then you will not be able to detect, right? So checksum will not be able to detect if you are having the same sum in each column. So that's how the checksum is working. Now you can calculate the checksum. Cool. So that is all about UDP. UDP is very simple. There is nothing to explain in UDP. Like we can just explain checksum, which I have just did. Now in TCP, we are going to study few more very interesting things, and then you will just appreciate the beauty of TCP. I mean, there are different implementation. I will make sure that you understand everything very clearly. So in TCP, we are going to understand what is like how we are going to do flow control, how we are going to do error control. Actually, this is, we have just explained, this is just a checksum, okay, and how we are going to do congestion control, which is very important. So these three topics, effectively these two topics, and if I just say, then this is the major topic that we want to discuss, because the flow control is just using the window. I will explain that how do we do flow control, but this will not take much time. Majorly we will be focusing on the congestion control because it is a bit lengthy topic. And then once everything of this is finished, then we will be talking about TCP timers. And at the last, we will be talking about token bucket and leaky bucket. And obviously, we will be talking about the connection establishment and these things, right? So in TCP, we are going to discuss all of this. Let's just get started. So, sorry. Yeah. So TCP is a communication which is a full duplex communication. So let me just show you the slide. Yeah. So TCP is a full duplex communication. What does this mean? It means that whenever you are sending a data, then this data, whatever you are sending, let's suppose you are sending from client to server. You are sending from client to server. Then whatever you are sending, it does not mean that only you can send. So basically client and server both are enabled to send, even though let's suppose there is some application where you do not want the server to send something, or you do not want client to send something, right? Let's suppose, okay, then in that case it doesn't mean that you can you can just open a one-way connection. You have to do a full duplex. There is no choice, okay, you have to do a full duplex, which means client generally in most of the cases, what do happen, client is sending some request to fetch something, and server is replying to your request, gives back data. Okay, this is a general scenario. Let's consider a case where I have a client. Okay, let's say in my laptop I just want to demonstrate the client and server communication, and I made a file which is basically, I made a C program file which is client.c, and there is another file which is basically saying that server.c. Okay, server.c. I mean, I'm just giving you one example. Let's suppose that I did it, and there are libraries in C program that in the C programming that basically support that how to communicate between client and server. So let's suppose I did client.c, which is very simple program I can easily write, and the server.c. Now, what I need to do to communicate between these two, let's suppose there is some particular application that I want to develop, and just to demonstrate that as a toy example, what I did, I will send a file name. Okay, I will send a file name, file path, basically file path to server, that I'm interested to read this path, this file. Let's suppose the client is saying that this is the file name that I'm interested in. Okay, and that obviously that file is stored in my computer, right? There is a file name that client will send, and then server has to reply. For example, server has to reply the content of the file. Okay, let's suppose this is a very toy example that we want to communicate. Okay, now what we need to do here we need to write two programs, client.c and server.c. Now tell me, just for like this is just a very normal question. Now tell me, if I just finish writing these two programs, then I have to run obviously these two programs simultaneously, right? Which means I will be opening one terminal. I will be opening terminal 1, terminal 1, and I will be running the client.c here, right? I will be opening another terminal, okay, terminal 2, or in Windows it is CMD, I think it is CMD, from terminal 2, and then I will be running server.c here, right? Now just tell me, here I am running client.c. I mean, I need to run the client.c, but let's suppose I have not started running yet. I need to run client.c. I need to run server.c here. Okay. Now suppose that I want to facilitate this communication, which means I have finished writing client.c, I have finished writing server.c, and my task is that client is asking some file and server will return that file. Okay, the data of that file. Now tell me that if you have two files, which is client.c and server.c, which one you will run first? Okay, I mean, obviously you need to run one of them first and then you will be starting another one. So do you run client.c first or do you run server.c first? See, once you run the client.c in the terminal 1, then only you will go to the terminal 2 to run the server.c, or vice versa. First you run the server.c and then you put the command to run the client.c in the another terminal. So which terminal do you use first, client.c or server.c? So skill enhancer is asking, sir, UDP is used for multicasting, video streaming, etc. In the network layer, IGMP protocol also use the same. No, I don't think there is any relation. IGMP is another protocol which is basically used for the multicasting grouping, and UDP is just because it is it is basically unreliable protocol. So there is, I don't think there is any relation. Obviously the UDP, that IGMP packet has to be within the UDP. Okay, so server you need to run first. Sumant is saying the server we need to run first. Why? Because if you run the client first, then the client will be immediately asking. See, this is just a fraction of second. It is not like after 1 minute client will be asking. So basically, if you run the client first, then client will be immediately asking to some request to server, and by that time, you are just about to run the server, right? I mean, the server is it just turned off. Just server is not yet started. So basically, if you run the client, let's suppose this is client, this is server, and if you run the client first, and server is not yet on, okay, server machine is like, for example, is turned off. If you run the client first, then it will be asking for some data, like give me this file. Okay, it will give the file name, and so it will be asking to the server that give me this file, and the server is off, right? So server will not be able to listen this request. So that's why you need to run the server first. So that's why we say the server is always running. Okay, basically server is always running. We assume that server is always running, and we call it passive listen, which means it is basically listening. Okay, it is always in listen mode. So server is always running. Whenever some client wants, then it can communicate with the server. So this is just one example that I wanted to give you. Okay, now let's just continue. Now here TCP is full duplex, which means there is a client, there is a server, and both are communicating. It is a byte oriented protocol, which means you will be counting every byte. Okay, so the sequence number here is basically byte oriented, which means like for every byte you will be giving the sequence number. For every byte we give sequence number. Now let's just move further. So there are two processes. This is sending process, this is receiving process, and TCP want to communicate between these two. Then you can easily communicate, and this communication is basically has to be the connection oriented, which means you have to establish the connection first. Okay, establishing the connection means that you will allocate, like I mean, before sending some data or before asking some data, client and server get to know that there is someone who is going to ask me the data, or there is someone who is going to reply me with the data. It's not like that you just throw away the data and you just ask something or something like that, right? I mean, you just want the other party that I want something, so that the other party get ready by that time. If the other party is not ready, then the other party will tell that, okay, I cannot establish this connection. So connection establishment oriented means that you are just warning the other party that, okay, I want to have some communication, that's all, so that the other party can allocate required resources. That's what connection oriented mean. Resources means buffer, maybe, okay, maybe allocated buffer, or whatever resources it wants. And maybe let's suppose that if it is not ready with the data, okay, data itself, let's suppose server wants to reply some data and it is not ready with the data, then it has to be ready with the data, right? So I mean, client can ask anything, so like that. So it will be actually bound, it will be prepared. So connection oriented means being prepared. That's all connection oriented means. Okay, Now let's just see that like this is the connection oriented. Let's just see that what other service the TCP provide. So TCP is basically reliable service, which means I will be sending acknowledgement if I receive something successfully. So it uses the acknowledgement. UDP doesn't use the acknowledgement because it is unreliable, just like IP. Okay, so we send, reliable means we send ACK on successful receive. Good. Now you know what is the numbering system, you know sequence number, you know acknowledgement. Okay, so I mean what is the acknowledgement number? Now let me tell you that okay, this sequence number, you know, we will be basically doing it with more examples. I mean we will be solving the gate P package. From that you will get to know much better. So but let me quickly tell you that what is the sequence number. So basically let's suppose you are sending let's suppose the initial sequence number you choose randomly. Okay, and let me just ask you one question. Let's suppose you are sending with the sequence number, you are saying that it is maybe 100. Okay, and let's suppose you are sending some bytes, which could be anything, which could be, let's suppose you are sending 300 bytes. Okay, in one go you are sending the 300 bytes, and let's suppose that this server or the client, whatever, it is acknowledging that okay, it has received the 300 bytes. Now you send again some bytes. Now can anyone tell me what is the sequence number here? If you are sending again bytes, see, if you just send one byte, you need to add 0, right? I mean if you are, let's suppose, sending one byte, then sequence number is 100. If you are sending two bytes, right, if you are sending, let's suppose, two bytes, this sequence number is 100, this sequence number is 101, and the next sequence number will be 102, right? If you are sending two bytes, then next sequence number is 102. Now if you are sending 300 bytes, then what is the next sequence number that you will be writing here? It will be 400, right? It will be 400. Basically for every byte there is a sequence number, so that's why it will be 400. I hope you understood. Now let's just continue that that how does this sequence number and acknowledgement behave. Okay, let's just see. So this is the sequence number. This is an acknowledgement number, is basically the next acknowledgement that it is expecting. So here it will say the acknowledgement is 400. 400 means now it is expecting a sequence number to be 400. The next byte it is expecting. So acknowledgement says the next byte it is expecting. Next byte it is expecting. With every ACK, you also send some receiver window size, which means that I will tell you in the flow control, but which means that I am expecting 400, byte number 400 to start with byte number 400, but it also tells that what is the maximum that you should be sending, which means if you are sending with the sequence number, okay, let's suppose you are sending sequence number 300 or the 100, and you are sending 300 bytes in total, then it will say that okay, the next which I am expecting ACK is 400, and whenever we are sending ACK, which means what we are expecting next is basically 400, then always we send, okay, with ACK, always we send, that is called receiver window. Always send receiver window, RWND. Let's suppose I am saying this is 700, which means I am saying that you start with 400, but maximum you can send 700 bytes. That's all. Okay, it doesn't mean like see, if I do not send this receiver window, then obviously the sender does not know that how many bytes to send. So that's why if I'm sending acknowledgement number, then I always have to send the receiver window. Like this is my maximum capacity that I can hold at this present. Okay, good. Now let's see the windows in TCP, that what are the sending window, what are the receiving window. So basically there are a sending window, there is a receiving window, because sender is sending some data and receiver is receiving some data. So there is a sending buffer and there is a receiving buffer. So what I am doing here, let's suppose this is the sending window. I am saying that this is the first byte, that is the first outstanding byte, which means let's suppose that I have sent these many, I have just sent these many bytes. Now I am about to send this byte. Okay, I am about to send this byte. Now once I receive the acknowledgement for these bytes, then I will shift the window. I mean currently I cannot send, it is just like a selective repeat. So let me just tell you that what happens. So I say, let's see, this is my window, and I divide this, let's suppose for example I divide this window into maximum segment size. Let's suppose these are the 4 segments in my window. Now I will say that see, like just like a selective repeat or go back, and I will say, let's see, this is my window, I am sending it to you, then now what you need to do, you basically have to acknowledge me whatever you have received. So suppose I am sending these 4 bytes, and and the window size is 4 bytes. Okay, window size is 4 segments. So I will say I am sending you 4 segments. Once you receive the 4 segment, I will send you something else. So let's suppose you get the ACK for this segment. You get the ACK for this segment. So you will be just sliding your window, and you will be saying that okay, now you can send you can send one more MSS, right? So that's how you do. So basically this is just a sliding window, and it also uses the acknowledgement, which is the cumulative acknowledgement. So basically, like in the TCP, what happens? ACK is cumulative. So actually this is very much implementation dependent, but in most of the implementation it is cumulative. Okay, for our gate purpose it is cumulative, but there are some modern TCP implementation which are also using the selective acknowledgement. Okay, but let's not worry about it. So that's why I'm saying in TCP many of the things are implementation dependent, but they will give you, okay, don't worry, they will give you that it is a cumulative, this is selective or not. Now let's just see that how does it behave. So suppose that you are sending initially 1 2 3 4. Okay, initially you are sending, the window size is, let's suppose, 4 bytes, 4 segment 1 2 3 4 5. Okay, let's suppose the window is initially the 4 segments, and you are just sending the 4 segments, and this is what you have not sent yet. So let me maybe draw a diagram clearly. So initially you are, let's suppose, sending 1 2 3 4, and then there are other segments also which you have not sent yet, but you will send once you get the ACK. 1 2 3 4. Okay, now your window is this much only. You have sent this. Then after receiving the ACK, you will send others also. Let's suppose that you receive, let's take a very simple example, you receive the ACK for this. Then what you will do, you will just shift the window and you will say now you can send this one also, right? The moment you keep on receiving the ACK, you will keep on shifting. But since you are using the sliding window here, the selective repeat protocol plus cumulative acknowledgement, which means you if you are getting, let's suppose, the ACK, let's suppose you are getting ACK for this, then you will be shifting the window. Then let's suppose you immediately get the ACK for this. Okay, it means that everything till this point has been received. Everything till this point has been received. So from the sender side, just look at the sender. If the acknowledgement is cumulative, then if whenever you receive any acknowledgement, you will assume that everything till this point has been received. Okay, I hope you understood this. So cumulative acknowledgement means whenever you receive something, then everything till this point has been received. So this is at the sender side, but at the receiver side, let's just see what happens. So you are using selective repeat. I mean, actually not exactly selective repeat, but because you are using cumulative ACK, so you can say that the windows at both the end is actually it is of some segment. It's not like the window at the sender is only one or that the receiver is only one. So windows are basically more than one. I mean, it could be anything at the sender, at the receiver also. Okay, so basically here, let's suppose the window is 4, and let's suppose for example here is also window 4, which means it can also receive 4 segment at a time. Now you are sending, let me tell you what does happen. This is 1 2 3 4. You are sending 1 2 3 4. Okay, so you are saying that like for example you have sent 1 2 3 4. Now by chance, let's suppose that this 3 is lost. Okay, by chance, let's suppose 3 is lost. At the receiver side, you will be getting 1 2 and 4. You will be getting 1, you will be getting 2, you will be getting 4. Now tell me, what is the acknowledgement that you will be sending? Will you say that you have received you have received till 4 or till 2, because you need to send the cumulative acknowledgement? So what you will say? You will say that you have received till 2 only, right? Because if you say that you have received till 4, then it will be a problematic situation. Got it? So basically you will say that ACK is basically, I'm just giving you some overall picture. You will say ACK is 3. ACK 3 means that you have received till 2. Now you are expecting third segment. I mean, it will be some byte number, but I'm not writing the byte number, but I hope you understood, right? So expecting third segment. Now it will send from the third segment onwards. So basically it will send 3 4 again, 3 4 again. Now 4 has already been received, but that is okay, that's not a problem. Okay, so it is basically using the window sizes more than one. I mean, it is actually in the bytes, but it could be anything more than one. Obviously, MSS generally it will be, and then you are using cumulative ACK. Okay, cool. Let me know if there is any doubt here. So basically, it is very easy. Whenever you are using cumulative ACK, you have to be careful. You cannot say that you have received till 4. That is all. That is the only point that I want to convey here. Okay, and the window sizes could be more than one MSS. So basically, I will just suggest you to do not relate it directly with the selective repeat or go back in, because it is combination of both, right? From the selective repeat, it is taking the window sizes, and from the go back end, it is taking the ACK part, right? Here it is using best of both. Basically, it is using window sizes more than one here, and it is using cumulative ACK from here. So it is mix of both, right? Cool. Now at the receiving window, at like what you will say that you have received this 20 to 260, and next byte to be expected to be received is 261. So this is how the receiving window looks like, right? Now in between there might be the case, actually in between you might have received something else also, but that will not matter to you. I mean, because the sender will again anyway send the all of the bytes, because you will just tell the start byte that is expected to receive. So let's suppose you have received all of this, and you have received this also, but that is okay to you. I mean, because sender is again going to send. So yeah, there is a repetition, but that's how the TCP works. Okay, maybe you have understood. Maybe let me just take one more example and let me tell you more clearly that how does the TCP work. Okay, and after that we will be just talking about the TCP header. So let me talk about the TCP flow control. So TCP flow control deals with all of this situation that I am just telling, which means that TCP flow control, now we are going to talk about the TCP flow control and TCP congestion control, and the first thing that we are going to say is TCP flow control. So TCP flow control basically deals with all of the things that we just talked about, which means it will deal just at the end to end. Okay, it deals with end to end flow only. Why I'm saying only? Because it does not take care of the congestion in the network. So basically, TCP flow control is very different from data link layer flow control. Why? Because at data link layer, I mean at data link layer, what we need, this is some host A and this is some host B, right? So at data link layer, it is only responsible from host to host delivery, right? From here to here. And let's suppose that I am sending a data to some host C, which is far away from host A. Now at the data link layer point of view, I am just concerning about the host A to host B delivery. Once the hope to hope delivery is final, then it will send the ACK, which means once from host A the data has been reached to host B, it will send the data link layer ACK. At the data link layer level, it will send the ACK. Do you remember that MAC addresses are keep on changing? In one of the question, I think in one of the CN test, I have put this question. So the MAC addresses are keep on changing, but IP address does not change, right? So MAC address keep on changing means data link layer is only responsible for hope to hope. So here you do not take care about the total congestion. But at the transport layer, the ACK goes from this host C to host A directly. This is the ACK at transport layer. So here you do not need to only care about this host A and host C, you also need to take care about this congestion in the between. So we have divided this into two parts. One is basically taking care of host A and host B flow, which is called flow control. Another one is basically taking care of the entire congestion, which is called congestion control. So let's first talk about the flow control, where let's just ignore the entire congestion in between. Okay, I will just talk about the host A and host B and how they are communicating with each other. which means that host A will tell its own requirement, host C will tell its own requirement and its own buffer. So that's what the flow control mean. Okay. So let's suppose there is one sender, there is one receiver. Now I want to demonstrate you that how does the flow control happen. So this diagram is going to be for the flow control. Now before this point, if you have not understood anything, then it is fine. Okay, there is some question. Sumant is asking, in IP header we have the total length, then why we need the total length field in UDP? Okay, I will come to that. Let me just continue with the flow control. I will come this question. Okay, so before this particular flow control, if you have not understood anything, which means you have not understood how the acknowledgement is working, how the buffers are working, that's perfectly fine, because now we are just going to start this flow control topic. Now here you will actually get to know what is the flow control, and then we will talk about the congestion control. Then you will get to know the difference between the flow control and congestion control. And in the congestion control there are many interesting things, and I will make sure that you get the crystal clear clarity of everything. Okay, so let's talk about the flow control. And before that, let me know if you have any doubt related to the acknowledgement or whatever we have just talked about. I mean any doubt in the topic that we have talked about. Okay, so let's just continue then. Now let's talk about the flow control. So in the flow control, let's assume that we have a sender and we have a receiver, and sender is sending some data and receiver is receiving some data. Now the communication could be in both the ways, which means the sender and receiver both can work as a, I mean the one host can work as a sender and receiver, another host can work as a sender and receiver both, because TCP is full duplex. But for this example, for this purpose, I'm assuming that there is one sender, this is going to be received. Okay, now I mean obviously once you understand one-way communication, like the same thing you need to repeat for the two-way communication also. Now suppose that the like it is basically in the connection establishment phase, and then let's suppose that they first want to establish the connection. This is the first step that they will be doing. So we will be doing it in two steps. One is the connection establishment, and another one is a, once the connection establishment is finished, then data transfer. Suppose that sender is sending some data, and that sender wants to establish some connection, and for that purpose, let's suppose that that they are saying that sender is sending some request to it, and initially it will send the SYN packet, right? That will be containing some initial sequence number. Let's suppose the initial sequence number could be anything. I mean you can take it anything, but let me take it 100. Okay, let's suppose this is 100, which is randomly generated. Now receiver will say that, see, I'm expecting I'm accepting your connection, which means the receiver will say that okay, I'm ready to receive the data that you are going to send me, and then I'm going to like just to acknowledge, it is going to say that I'm going to acknowledge your packet, and my acknowledgement number that it is going to say is basically, can anyone tell me what should be the acknowledgement number? See, SYN you are sending, so it will be consuming one sequence number. So it will say that my acknowledgement number that I want to send, like that I'm expecting, is basically 101. Okay, it will say that it is 101. I hope that is fine to everyone. But since TCP is full duplex, it will also say that I also want to establish some connection with you, which means it will not only send the ACK packet, it will send the SYN plus ACK. So it will also generate some random sequence number at its point. Let's suppose this is 1000. Okay, SYN, and the initial sequence number that it is sending is, let's suppose, 1000. Is this fine to everyone? Let me know. Okay, so let's just understand this TCP very clearly, right? So this is fine. Now it is going to send the ACK, right? Is this okay? This is SYN packet. This is what we call SYN packet, and this is what we call SYN plus ACK packet. SYN plus ACK packet, and then it is again going to send the ACK. These are the three steps in which we do the connection establishment. Now, as I told you just 5 minutes ago, that whenever you are sending the ACK, you just not only send the ACK, you also send something called as receiver window size. You also tell that okay, I am expecting the next byte to be whatever it is. Let's suppose in this case it is 101. It says that I am expecting next byte which is 101. but my receiver window size is 800, which means I'm going to say that my receiver window is going to be 800 or something. Okay, it also tells us, always tell with the ACK, it always tells the receiver window. If you want, you can make a note of it. Whenever we send ACK, we always send or advertise a receiver window, because ACK means it says that this is what I'm expecting. As next bytes, right? Receiver window says that this is how much at max you can send me this much. These many bytes. Hope you understood, right? Okay. Now let's just continue. This is the receiver window, and then it is sending the ACK. So can you tell me what is the ACK it will be sending? It will be sending ACK which is 1001. And now since it is sending ACK, it will also send RWND, which means it will say, see, I am going to expect next which is 1001, but my receiving window size is something. I mean, it could be anything. Let me just take it maybe 600 or I mean whatever. So you can take it anything. But since I'm just telling you the communication from sender, I mean I'm just assuming this is a sender, this is a receiver. So let's not worry about it, okay? Because for this particular example, I'm not going to concern that it is going to send. I mean just for this particular example, okay? That's why otherwise I mean it will be sending because it is full duplex. It will be sending some receiver window. But for this particular example, I'm not much concerned about this receiver window. Okay, so I hope that's fine. Like, have you understood what I'm just saying? See, what I'm saying here is that it is some client, it is some server, and communication is a both way. So whenever you are sending ACK, you will also send the receiver window. But for this particular example, I'm just going to assume that this is just a sender only. Okay, so that's why this receiver window I'm not writing, although it is there, but I'm not writing. Anyway, you have understood, right? I mean the communication is in the full duplex. So since it is only going to act as a receiver, that's why I'm just going to say that this is a receiver window. Okay, it will send SYN, then SYN plus ACK, then ACK. So this is the connection establishment phase which is done. Now let me just copy this connection establishment phase. Okay, this is a sender receiver connection establishment phase, and then let's just start the data transfer then. Okay, so let's just copy it on the side. Now the data transfer will happen. Now from here the data transfer will happen, right? So this is sender, this is receiver, and now the data transfer will happen. So this is the most crucial step that we are going to see in the flow control, that how do the window sizes works and how do the acknowledgement work, right? Now let's suppose that I say now I say that there is some data that I'm sending. Now based on this previous interaction, can you tell me that what should be the sequence number here for the data based on the previous interaction that I just told you? See, it is just expecting 101, so I will say that I'm sending you 101, right? So this is the data I'm sending, and then it will say that how much data. I mean it will be some data, so it will also say that how much data it is sending. Let's suppose that I'm sending some data which is suppose maybe any number of bytes. Suppose this is 200 bytes. Okay, so the data that I'm sending is, let's suppose, 200 bytes. Cool. Which means that here at the sender I have some sending window, right? I have some sending window, and I'm going to say that the sending window could be, see, it is saying that it can expect, you can send me at max 800, but currently I do not have, let's suppose, 800, and I just have 200 bytes, so I'm sending 200 bytes. So there is a sender window. Let me just show you that how does the sender window behave. Okay, so this is the sender window, and let's suppose the sender window or sender buffer, this is having some number of entries, and here I'm saying that sender window sizes, it could vary, but let's suppose it is starting from, okay, the byte number that is starting from is initial sequence number is 100, right? So it is starting from 101, which means the first byte here is 101, and I will be receiving, I mean, this sender is basically some buffer. It will be receiving some data from the application layer. So till now, I have just sent 200 bytes. Okay, 101 to 200. So these are the 200 bytes I have just sent. Okay, this is just sent. Okay, 200 bytes, which means this is 300, byte number 300. Till byte number 300, I have sent. I have just sent this. Okay, this sending is done. Now I am having from byte number 301, from byte number 301 to some bytes that I'm having. Let's suppose that that the sender window size is some number of bytes. It could be anything, but let's suppose the size is 800 or 900, or it could be anything basically. Okay, let's not worry about it. So basically, the current situation is that these are the 200s, or like I could have sent 800, but this is the only available data that I'm having currently. Okay, so that's why I have sent the 200. Now it will receive this 200, right? So receiver will say that okay, I have received the 200. Now I'm expecting the next byte number. Okay, ACK, it is going to say ACK is 301. Very easy. But whenever you are sending the ACK, you also have to send something called as receiver window. So let's suppose here, this is the receiver window size. Here it has just received the receiver window size. It has earlier advertised 800. So it will say it is the 800 bytes, which is the first byte it is expecting was 101, and till the 800 it was expecting, right? Till 800 it was expecting. Now I have just sent you some bytes till 300. Now basically I have sent you 200 bytes. Now this is the 600 bytes which are remaining, right? I mean, now I'm expecting 600 more bytes. So basically this is the byte number which is 301. I mean, numbers does not matter. What I want to say, that sender has some data to send. It can send within the limit that the receiver can expect. So receiver can expect at most, expect at most 800. I am sending 200. That is fine. I am sending just 200 bytes of data. Now it has received 200. Now it can take the 600 more. So it will say now my receiving window size is 600. Let me know if that is clear to everyone. Okay. Okay. Sequence number for last ACK is 1001, right? Because this is the initial sequence number you have. So SM Arif Ali is asking that what is the sequence number of the last ACK in 3-way handshake. So sequence number is 1001. So basically this flow control is very easy. I just want to convey one thing, that whatever you are advertising, right? Whatever you are advertising, this is 800 you are advertising. I can send you at most 800. I am sending 200. Now remaining is 600. So that is fine. Now I am sending, so give me 600. Interestingly, this remaining could be more than 600 also, which means by that time you are sending me this 200 bytes, I am saying now my buffer is actually more than 600. Let's suppose this is 800 or something like that, right? Let's suppose this has been increased, which means I can send either 600 or maybe more than 600. So anyway, it is receiving 600. So now you can send at max 600 here. So whatever you are sending, let's suppose the next sequence number you are sending is 301, and data you are sending, you can send at most 600. Let's suppose you are sending 400. Okay. So it is very easy. You are sending 400, and then it will be receiving the 400 more. So which means it will be receiving 400 more. So it will say that now I have received the 400 more. Now I'm left with 200 only, right? So it will say that okay, I'm left with 200, which means I have received this, I have received this. Now this 200 is remaining. Now maybe by that time that this data has been consumed, and then its buffer may increase. So it will not only just say that okay, you just send me 200. Okay, it will not say that okay, RWND is 200. It may get also increased. That's the point, right? So just to summarize, let me tell you what do I mean by that. As a summary, sender is going to always send the data, send data lesser or equal to RWND, receiving window, and this receiving window that I am going to advertise could be anything, right? I mean, it could be anything, depends on what do I have currently. Could be anything. You can say it could be anything. I can advertise anything actually. There is no rule here. Could be anything. So that's how this flow control works. So I am always going to send whatever receiver going to can expect. I can always going to send lesser than that. That's how the flow control works. Okay. So that's the summary of the flow control. I mean, I'm going to send whatever the receiver can expect, lesser than that. Now let's just continue. So okay. So these are the this is the diagram that I have taken from Frozen, which is just telling you the flow control. Now let's just continue to some questions, and then we will talk about the congestion control. So let's solve this question, which is very recent question, has been asked in 2021. Now what they are saying, consider a three-way handshake mechanism during the TCP connection establishment between P and Q. Let X and Y be the two random 32-bit starting sequence number chosen by P and Q respectively. Suppose P sends a TCP connection request message to Q with TCP segment having SYN equal to 1 and sequence number is X. So basically whatever you are sending here you will say that SYN is 1, which means this is a sequence number, and I mean this is the first packet. SYN 1 means it is the first packet, and sequence number you are sending here is X, and the ACK is 0. ACK bit is 0. ACK bit is 0 means this is just a SYN packet. Okay. Suppose Q accept the connection request. Which of the following choices represent the information present in TCP segment header that is sent by Q to P? So they are saying what you are going to send from Q to P. Very easy question, right? So this is P, this is Q. So what will be the SYN? SYN bit will be obviously 1 because this is the first packet from Q. So that's why SYN bit will be 1. So B is not obviously the correct answer. Now since you are sending the sequence number X, so it will consume the sequence number. So that's why for the ACK, it will say the ACK is X plus 1. SYN always consume one sequence number. So which means that it is going to send the ACK as X plus 1. ACK is also 1. SYN is 1 because it is SYN plus ACK packet. So SYN is 1, ACK 1. So either C or D is answer, and ACK will be X plus 1. That's what we know. So that's why C is the correct answer, right? So this question is very easy. Now Pushpesh is asking, sir, what is meant by the statement the SYN or FIN increments sequence number by 1 and ACK increments sequence number by 0? Which statement? So okay, I do not see this kind of a statement here, but maybe you have read it somewhere else. So let me just address this question. So Pushpesh is asking, let me just copy this question on the slides, then I will just answer. So by the way, this is right? So SYN the C is the correct answer. So before I move to the next question, let me just address one of the questions that is asked in the chat window. So Pushpesh is saying, sir, what is meant by statement that SYN and FIN increment sequence number by 1, ACK increment sequence number by 0? Okay, maybe you meant in the connection establishment phase. What happens? Let me just tell you. See, whenever you are sending some request, then this is first packet, which is SYN. Now since it is having some sequence number, let's suppose the sequence number is X, right? Now this packet will consume, okay, increment means consume. So this packet will consume one sequence number, which means that here the next time we are going to send any data or anything, then next time you are going to say that, see, now whatever I am going to send the next time, it is going to have the ACK, the sequence number. The sequence number will be basically from X plus 1 because X I have just consumed here. In other words, that I am going to, or the receiver is going to acknowledgment, and receiver is going to say X plus 1, which means receiver is now expecting X plus 1. So you are also going to send X plus 1. So basically you have wasted one sequence number because of the SYN packet, right? You have not sent any data here, but you wasted one sequence number. So that's what we call increment. Okay. Similarly, in the FIN also happen. I will tell you, but let's just understand with the SYN. So basically, you wasted one sequence number here because here you cannot use sequence number X again because receiver is expecting X plus 1. So you have to use X plus 1. So you wasted one sequence number here. Let me know if you have understood this. So that's why we say that SYN always consumes one sequence number. Now let's talk about the ACK. Okay, Let's talk about the ACK. Now you send some SYN packet which is basically has let's suppose sequence number X, and then you send here some SYN plus ACK. Okay, which means you are going to select some sequence number which is, let's suppose, Y, and you are going to say you are going to expect some ACK which is X plus 1. Okay. Now just see here carefully the third packet you are going to send ACK. In the third packet, let's suppose you are not sending any data, just a ACK, just a vanilla ACK. You are just sending a ACK, not a piggybacking ACK. Okay. So if you are sending this ACK, then you will say, see, I am not sending any data, and I'm just going to say that ACK is Y plus 1. Now tell me, does it have to have any sequence number? Will it going to consume any sequence number? No, right? What do I mean by that? I mean that whenever next time you are going to send the data, what will the sequence number of the data? The next time you are going to send the data, let's suppose this is a data transfer. This is the connection establishment. Now next time you are going to send the data, it will be what it will be. It like sequence number will be X plus 1 only, which means you have sent this ACK, but it is not consuming any sequence number, right? ACK, just a vanilla ACK does not consume any sequence number. See, here you are consuming one sequence number because next time whenever you have to send the data, you are sending with with X plus 1. You cannot send with X, but here you are not consuming any sequence number. So basically ACK does not consume any sequence number. Okay, so ACK, if you are not sending the data, if you are obviously sending the data, then it will consume the sequence number. But just a vanilla ACK, not the piggybacking ACK. Okay, ACK does not consume any sequence number. Any sequence. That's what it means. Now similarly, whenever you are going to send the FIN packet, okay, you are going to send a FIN means that the connection termination. Then since you do not send any data generally, okay, with the FIN packet, although you can send, but generally we do not send any data. You just send that FIN, and then there will be a sequence number. Then it also has to be acknowledged, right? So whenever you are sending FIN, let's suppose the sequence number is 3000. Since it has to be acknowledged, that's why this acknowledgement number will be 3001, and then you will say that okay, see, you do not send any data further, but it has actually consumed one sequence number, right? Because the sequence number here is 3000, but the next sequence number, although you cannot send, but actually it has consumed one sequence number because the acknowledgement is 3001 now. It is about whether you are consuming some sequence number or not. So let's just understand more question, and maybe you will be having a clear cut idea by the questions practice. So let's see this question. Consider a TCP connection in the state where no outstanding ACKs are there. The sender sent two segments back to back. The sequence number of the first and second segment are 230 and 290. So this is 230 and another sequence number is 290. They are sending back to back two segments. The sequence number of first and second segments are this. The first segment was lost. Okay. Yeah, this is going to be interesting question. But the second was received successfully. Now tell me, at the receiver side, as I told you, it can expect the it can accept the out of order packet. That's not a problem. So which means, let's suppose there is the first segment which is lost, but this is the second segment which has been received, which is basically having the sequence number that is starting with 290. So from the byte 290, this is the 290th byte. I am saying that this is what I have received, but this is what I have not received yet. Let X is the amount of data carried in the first segment, and Y with the here the data bytes are X, and Y with the ACK number sent by the receiver. So it is going to say, let's suppose ACK number is Y. Thus, tell me the value of X and Y. Let me know what is the answer here. This question is very nice. Okay. Since TCP uses the cumulative ACK, I mean they should actually tell it, but I think this is the question from 2007, and by that time the TCP used to use only cumulative ACK. But nowadays, I mean in very recent implementation, they also use the selective ACK, but it is not in the GATE syllabus. So by default, we assume that TCP uses the cumulative ACK. Let me know what is the answer that you are getting here. So I'm just waiting for a couple of seconds so that you get the answer. Okay, Sumant is saying 60 and 230. Yes, that is the answer. So why? See, here although you have received it, but you use the cumulative ACK. That's why you cannot send the you cannot send the data, or you cannot send the acknowledgement acknowledging this. You have to say that you are still expecting 230 because 230 is lost. So you have to say you are still expecting 230. So that's why ACK is 230. And how many bytes you are sending here? Since this is 230 byte number, this is 290 byte number. That's why data bytes you are sending here is 60. So 60 and 230 is the answer. Right? So D is the correct answer here. Okay. I hope you understood. Let me know if there is any doubt in this question. Cool. Let's just move further. Now let's have a quick discussion about silly window syndrome. There is one problem with with the TCP. Basically, it is called silly window syndrome. It's very easy, but let's just quickly discuss it, and then we will solve more questions. So basically, in the flow control, I hope you understood everything, and this question actually clarify one of the thing which is out of order segment. If you receive something out of order, then you can basically accept it. That's not a problem. You can accept it, but you have to send the ACK for this one only. Okay, that you are expecting now this particular segment. Okay, this particular segment only you are expecting. Cool. Now, what is a silly window syndrome? It's a very silly thing. It says that you have a sender here, you have a receiver here. Now, suppose that sender is very slow. Okay, there are two cases. One is that sender is very slow, which means it is the application layer here. Application layer is just giving one byte every time. Okay, every time. I mean, it is not filling the sending buffer with a large number of bytes. It is just giving one byte, dropping one byte here. Now, since sender is using TCP, what it will do? It will let's suppose what it is doing, whatever it has in its buffer, it is sending one byte. Okay, sending data bytes is one byte. Now, receiver will accept it. Receiver does not have any problem in accepting. But do you see a problem here? What is the problem in sending one byte? See, it is too much costly. I mean, this is just a data and header. Let's suppose you are using TCP, which is minimum is 20 bytes for TCP. And then you are using, let's suppose, IP, and for the IP also minimum is 20 bytes. And the data is just one byte, right? Data is just one byte. This is data. Obviously, it is not a good thing. I mean, just to send one byte of data, we are using 40 bytes of the headers. So that's not a good thing. So basically, if sender is very slow, okay, which means it is producing the data very slowly, then it is not a good thing to send one byte every time. So what could be the solution? I mean, there is no hi-fi mathematics that is required. You can just use the normal intuition. That is the solution here, and that is given by the Nagel. Okay, Nagel was one scientist, so he is given one solution. Gaurav is saying, sir, in selective repeat, you said when 3 is lost, then ACK will be sent for 3. But it is sending only 3, 4. I'm not getting. What is 3? What is 3? Actually, I am not. Please ask me a question which is related to the slide, or give me a reference. I mean, what you are asking. Okay, I cannot guess what is going on in your mind. Sumant is asking, sir, wraparound time will be discussed in today's session only. Yeah, there is one question. We will discuss that question. Okay, we will directly discuss that question. So now it is not a good idea. So what we can do, instead of sending one byte every time, I will say let's just wait for some time. So if sender is slow, okay, if this is sender which is slow, let me say it is a slow sender, then instead of sending 1 byte every time, not a good idea. So this is first of all not a good idea. So what it says, let's just wait for some time, okay? Let's just wait and send after some time. So it says that wait and send when you have enough data. That's the only solution. I mean, that's very easy solution, but yeah, that's the only solution that you have here. Okay. Now once you understand this, then there is a problem with this. I mean, you need to be very concrete that what do I mean by wait and then send the enough data. So basically, it says that you wait, but if you are having 1 byte, then let not receiver keep on waiting for you. So basically, this is a sender. If you wait good enough, then receiver will also waiting for you, right? So since receiver is also waiting for you, that's why you cannot wait a long time. So what you do, you basically wait enough time, which means you just use for some time, okay, just for some time. I mean, I should not be using that particular term, but just understand in that way, just for some time, you use stop and wait, which means that you send 1 byte, no problem, you send 1 byte, but you stop there. You do not keep on sending. As long as you have 1 byte, you do not keep on sending 1 byte, okay? So it's just saying that there is one solution that is proposed by Nagel. So it says that you do not keep on sending 1 byte, you send 1 byte and then stop and wait for the acknowledgement, which means receiver, in this way, receiver is also not waiting for you. Receiver will not think that okay, you have died, right? I mean, otherwise receiver will think that sender has gone. So basically, you send 1 byte and then wait, okay? By that time you will be having enough bytes. Now send 1 byte, wait. By that time you will be having enough bytes and then send 1 MSS. Send like window, whatever your window you have, right? So I mean, that's how it works. So it's very easy solution. Send your window based on the receiving window size, obviously. Right? So it says that you if you are getting 1 byte every time, so you do not keep on sending 1 byte. So this is the bad idea, that you keep on sending 1 byte, this is definitely a bad idea. It says you send 1 byte, not a problem. Then once you send just 1 byte, not keep on sending, and then wait. By that time you will be having enough buffer, then send the window. That's the only thing, right? Okay. So see here, this is the solution that is proposed by Nagel. So he says, so Nagel algorithm is very simple. He says the sending TCP first sends the first piece of data it receives from the sending application program, even if it is only 1 byte. So it sends the 1 byte, not a problem. It says that it first sends the 1 byte. After sending the first segment, which is even maybe just 1 byte, the sending TCP accumulates the data in the output buffer. Wait until wait until either receiving TCP send the ACK. So basically, you wait enough till you get the ACK, or till you get the enough data. Before the ACK, let's suppose in between also you are getting the enough data, then you can send. Okay, you do not need to wait for the ACK. So that's what it is saying, that till you get the ACK, or you have the enough data. I mean, you do not need to know much of the detail, to be very honest, but you just should be knowing what is the idea. So the idea here is that first you send the first packet, which is even 1 byte, then you wait for the ACK. Now by that time you will be having enough data, or maybe in between also, if you are having enough data, then you send that. If you do not have in between, then you send by the when you get the ACK. By that time you will be having enough data, then you do it. That's all the thing that it does. Okay, this is the situation when sender was slow. Okay, this is the situation when sender was slow, but it will be the situation when receiver is also slow. Sender is slow, but there might be a situation when receiver is slow. This is sender. What do I mean by the receiver slow? Let me just tell you. This is receiver and this is also slow. Okay, so whatever you are sending, let's suppose you have sent 200 bytes, or maybe more bytes. Let's suppose you have sent 800 bytes. Okay, for example. You have sent 800 bytes. And receiver, you have sent 800 bytes because let's suppose receiver is saying that initially you can send me 800 bytes. I mean receiver is saying that my buffer is empty. You just send me 800 bytes. I can eat up all 800 bytes. And you send 800 bytes actually, right? Now what will happen? This buffer is full, right? The receiving buffer is full. But let's suppose receiver is slow. Receiver is so slow, for the extreme case I am telling, receiver is so slow that it just eats up 1 byte at a time. Okay, it is not able to, that application process not able to consume more than 1 byte at a time. So it will say, after consumption of 1 byte, it will say that see, I now have a space of 1 byte, so you just send me 1 more byte. Now my receiving window is 1, right? And then you send 1 byte. Then you will say that okay, now I have consumed 1 more byte, you just send me 1 more byte. Is this a good idea? That it is saying that okay, you can send me 1 byte. Now sender will say that sender is eager to send, right? It is, let's suppose it is an eager sender. It is eager to send. Whenever it receives any sender, any receiving node, it immediately sends something. It is saying 1 byte, okay, it immediately sends 1 byte. So here the problem is, main problem is because of the receiver is slow. Receiver is just consuming 1 byte at a time. Now, how to rectify this problem? So for this, can you just think about some intuition? Yeah, again, wait for some time. That's the only intuition, right? I mean, wait till you have enough buffer. Wait till receiver consumes enough bytes. You keep on waiting, and like till the moment you are waiting, then you do not send anything, right? You just wait. I mean, just wait for the receiving just consume enough bytes. I hope you understood this. But now, do you see a problem with the waiting? So earlier also there was a problem with the waiting. See, let's suppose I say that the earlier when the sender is slow, okay, this sender is slow. Do you see there was a problem with waiting? That's why we have sent the 1 byte, right? So if you just wait at the initial phase, okay, initially if you just keep on waiting, you say that let's wait for this buffer to full, this buffer to get enough bytes. Let's suppose you say this, wait for this buffer to get enough bytes. The receiver will think that sender is died, right? Receiver will think sender has died, isn't it? So to remove this problem, what we did, we said that you wait, but not at the initial stage. I mean, just give him 1 byte so that he get to know that you are alive, and by that time he is sending ACK. Then you will be having enough buffer, right? So basically, you wait, not a problem, but just let him know that you are alive. Okay, just let him know you are alive. Basically, you are sending 1 byte of data. Now, similarly, here, if let's suppose the receiver is slow, okay, if receiver is slow, if I am saying that you wait till you consume enough bytes, okay, these are the many bytes you have. So this is the application process. You are saying wait till application process consumes enough bytes. But then the problem here is that sender will think that receiver has died, right? If you keep on waiting like that, sender will think that receiver died. So basically, what is the solution to this? What do you think could be the solution here? Now the solution is that the receiver will say that okay, I'm waiting like till I consume the enough bytes. So by that time, I will also send ACK, not a problem, so that sender will get to know that see, I have no receiver has not died. So basically, receiver will say that let me just send the ACK here, and with ACK I need to send the receiving window, right? Although my receiving window size is 1 or maybe 1 or 2 bytes, I mean very small, I will say 0. Okay, I will play a trick here. Although it is not 0, I will say 0. so that sender does not send me 1 byte. I make sure that sender does not send me 1 byte. Although my receiving window size is 1, still 1 byte, I will still say it is 0. So that sender will say that, oh, okay, you are alive, but you are full. Okay, so okay, let me just wait for some time till you get till you send me another ACK with another receiving window size. So basically, by doing this, sender will get to know that okay, receiver is alive. So you wait, not a problem, but let the sender get to know that you are alive. Similarly, here also, you wait, not a problem, but let the receiver let you know that you are alive, like that. So there are simple solutions. You do not need to remember that solution, that okay, what need to be done, what not need to be done. They will not ask you that okay, in the TCP what is the Nagel solution, and this is called if the receiver is slow, this is called Clark's solution. Let me just tell you this slide I have taken from Frozen. So this is called Clark's solution. There was another scientist. He has given the solution when the receiver is slow. Okay, he is saying that is send an acknowledgement as soon as the data arrive, but to announce the window size of 0 until there is enough space to accommodate the more data. So that's the very easy solution, right? You do not need to remember again, but you just need to make sure that that you have understood everything. So let me know if you have understood the things. Cool. Now let's just continue. So basically, this is called silly window syndrome. Now let me tell you how does the ACK behaves. As you already know, the ACK is cumulative, but let me just tell you a little bit more detail. Okay. So ACKs are cumulative. I mean, see, in today some TCP implementation also use the selective acknowledgement, but not for gate. I mean, that's not required for gate. Okay. So ACKs for gate, we will assume that it is a cumulative, and I have taken both of these screenshots from the Frozen only. Cool. Now, in TCP, typically, I mean, there are some set of rules that I have taken from Frozen, and using those rules only you generate an ACK. But those rules are very simple. Let me just tell you that what do happen. Suppose you receive some data. Okay, suppose you receive some data and wants to send ACK. Okay, which means that you wants to send ACK. Now, the question here which I'm asking is that, do you send ACK immediately whenever you want? Should you send ACK immediately, or it is better to wait for some time? Okay, so my question is that, do you send immediately, or better to wait for some time? Or maybe better to wait for some segments, like you will say that okay, after 5 segments only I will send, something like that, right? What do you think? What you will prefer? So, Sumant is asking, what if the wait time is greater than the timeout? Which timeout? I think he is asking here that you are waiting. Okay, maybe I don't know which timeout you are talking about. The transmission timeout you are talking about. Maybe you are talking about the time here. So if the sender is slow, you just send 1 byte, wait for the some time and till the ACK arrives. Which timeout? I mean, like I'm not getting the timeout, because timeout and these things comes when the ACK is lost, and then the timeout is generally triggered. So maybe I have not understood your question, because when ACK is lost, then only the timeout is triggered. Anyway, we will talk about the TCP timers today only. Okay, so you will get to know maybe more. So what do you think? What is a better idea? Actually, the answer is that like there are many things which are implementation dependent. Obviously, like it depends on the implementation. So answer is depends on implementation. You can implement in any way. Okay, depends on implementation. That's all. So if you want to send an ACK, you may send immediately, you may send after some time, you may send after some segment. Okay, it depends on the implementation. There is some set of rule that is given in Frozen, and they have also said that they have defined several implementation. There are many implementation. We give most common rules here. So obviously we do not need to know these common rules and all. Okay, I mean this is also implementation dependent. So basically I mean TCP is very easy protocol. Don't worry, I will make it very simple. At the end I will summarize everything. I will tell what is implementation dependent, what is not implementation dependent. Let me just continue for a couple of while. Okay, and then I will summarize everything that what you need to be knowing as a basics. Okay, this is the fundamental, and these things are implementation dependent. In whatever way you want, you can implement it. So I will tell you. Right now, let's move to most interesting part, which is TCP congestion. Let me know till now if you have any doubt. Let me know if you have any doubt before the TCP congestion. Okay, if this is clear, let's move to the TCP congestion then. So, as I told you that there are two things that we need to take care. One is the host. This host is sending some data. Let's suppose A to, let's suppose this is host B or host C, whatever, right? Host C. Now, in between, it is unlike of data link layer. In between, there is a network. There is a complete network here, right? Unlike data link layer. In data link layer, we need to just take care of hope to hope ACK, hope to hope delivery. Once host A, like at the data link layer part, it does not even know that it is sending to host C. The MAC address will be, let's suppose this is router. MAC address for the destination MAC address that the packet is traveling will be the destination MAC, will be the router R, right? So at the data link layer, you do not even know that you are sending a packet to host C. But at the transport layer, you obviously know, right? So in that case, the things become little more tricky. In data link layer, you do not need to take care about the congestion, but here you also need to take care about the congestion. So we have named it two things. One is flow control, which means we need to make sure that host C, okay, this host is ready to accept the things which I am sending, which is governed by RWND receiving window. Host will say that, see, from my end, I am telling you that I can expect, let's suppose I can accept, let's suppose 800 bytes. I can accept, let's suppose 800 bytes. Now it is also depending on the network. We will also ask the network, okay, what you can accept. If you cannot accept 800 bytes, let's suppose this host is powerful machine which is having enough resources, enough space, but the network is very much congested, then there is no point in sending 800 bytes, right? Because that will lost in the network, and that's very very bad implementation. So I will take care of the network also. That's called congestion. And since there in the network there is too many things, right? I mean there are too many routers, there are too many things. I cannot ask individually each one. I cannot ask each router individually, okay, what is your buffer, what is your buffer, because they keep on changing and there are too many. So what will I do? I will say, I will just predict it. Okay, what is the congestion in the network? How much the network currently handle? So that's called congestion control. Okay, so let's just see that how I'm going to do it. So basically, whenever the sender is sending to the receiver, then the bottleneck could be this routers in the between, right? So buffer overrun at the router. Then whatever you are sending, if you are sending much data, but the data is getting lost here, and you are delivering the less data. Bottleneck is inside the network. That's called congestion. I hope you understood that we need to take care about the congestion also. Okay. So let's just see that how to detect the congestion. As I said, like we need to detect the congestion. We cannot ask each individual router separately. So what we will be doing, we will be detecting the congestion. How? Obviously, if we are sending something, if it is getting lost, then it means there is a congestion. So congestion we will be detecting by the loss of the packet. Okay. So let me just write it here. Congestion detection happens by the loss of the packet. We can detect congestion now. Let's just see that how we do it. Okay, so TCP sender uses the occurrence of two events as a loss of the packet. Either there is a timeout or you receive the 3 duplicate ACKs, which means you can detect that, okay, there is a loss of a packet. how if you are sending something and you are not receiving ACKs, you are not receiving ACKs, which means it might have lost, which means there is a timeout, right? I mean, after timeout you will get to know there might be some problem because the timeout has occurred and I have not received the ACK, so there might be some problem. So you will say that there is a timeout. This is one thing, I mean, using which you will say that okay, there might be loss of the packet, right? I mean, you will be very much alarmed that okay, there might be the loss of the packet because of the timeout. Another thing is that you are sending some packet. Let's suppose you are sending multiple packets, but one of the packet getting lost. One of the packet getting lost. So in this case, the TCP at the receiving end will be sending the ACK for this packet only. It will be whenever it receives this, okay, whenever it receives this, it will be sending the ACK that okay, give me the packet 1. Okay, it will say the ACK equal to 1. Right, it will be the byte number, but just for the example, I'm saying ACK equal to 1, ACK equal to 1. So basically, whenever you are receiving multiple ACKs for the same packet, it means, and the packet has already been, it means that there must be a loss of the packet. That's called 3 duplicate ACKs. See, what do I mean by that 3 duplicate ACKs? You are sending some packet. Let's suppose this packet is lost, but subsequent packets are getting delivered. Then the receiver, at the receiver end, what will happen? Receiver, whenever the receiver gets this packet, okay, this another packet, which is this one, receiver will say that see, I am expecting the packet number 1. Receiver will say that this is ACK for the packet number 1. I am just expecting the packet number 1. Give me the packet number 1, right? Whenever, okay, so whenever you are sending some packet, receiver will say I am expecting the packet number 1. This is ACK 1. Similarly, when it gets delivered, receiver will again say I am expecting packet number 1. Receiver will again say I am expecting packet number 1. So basically this was the packet number 1. Then you will get to know that okay, packet number 1 must have been lost. Now why I am waiting for 3 ACKs, 3 duplicate ACKs, why not just 1? Which means if it is getting delivered, it will say the ACK 1, which means I am expecting the packet number 1. So maybe because just using one ACK, I'm not 100% sure that maybe because this packet is delayed, right? It might reach later also. So I do not know, it has been certainly lost. And then why not 2 ACKs? Basically there is no science behind it. This is just a human intuition that I mean, there's just a heuristic. Everything cannot be the science driven, right? This is just a heuristic means that this is just an intuition based thing, that okay, if this is 3, then it is not too long and neither too short. Basically for 2 also, my reasoning could be that okay, maybe these 2 packets are delivered, but maybe this is delayed, right? It might reach later. So that is my reasoning. But with the 3, it is too much to say that 3 has been delivered and this is delayed, so it is too much of delay then, right? So anyway, like this is just a heuristic that I'm saying that if I'm receiving the 3 duplicate ACK, it means 3 duplicate ACK tells me that the packet is lost, but the subsequent 3 packet has been received. So I will be detecting congestion either using the timeout or using the 3 duplicate ACKs. Then what is the difference between the timeout and 3 duplicate ACKs is that if this is the timeout, which means I am sending some packet and I am not receiving any ACK and there is a timeout, okay, there is a timeout. After some time I get to know the packet has lost, right? I get to know the packet has lost. I have not received any ACK. Which means if I am not receiving any ACK, it means the subsequent packet also has been lost, right? Subsequent packet also has been lost. This is also lost. So basically, timeout says that if you are not receiving any ACK, even for the subsequent packet also, that means all packet has been lost. Timeout generally indicates that all packet has been lost. Has been lost. And there is another situation using which also I can detect the congestion in the network, which is the 3 duplicate ACKs. If I am getting 3 duplicate ACKs, which means that the subsequent 3 packets has been reached, right? If I'm getting ACK1 here, okay, this is the data packet number 1. Actually this will be not the I mean, this will be having the sequence number, some sequence number, let's suppose 100, and ACK will be again and again for 100, ACK 100, which means I'm saying that I need a packet which is starting from 100. It means that there must be 3 packets that has been reached, okay, and I'm getting 3 duplicate ACK. So 3 duplicate ACK says only one packet has been lost, okay, so it says that only one packet has been lost. That's the difference, right? So I hope you understood. Why? Okay, so case is asking why it is called 3 duplicate ACK. Why it is called 3? I mean, because because these are 3. Actually, this is number. This is a count. Exact 3. This is the count 3. That's why I'm calling it 3. Because if I'm just getting, see, this is called fast retransmission. I mean, I'm not waiting for the timeout, right? I mean, before timeout, I'm getting the 3 duplicate ACKs. So basically, I need not to wait for the timeout. That's called fast retransmission. I can detect the congestion using the 3 duplicate ACKs. So this is the absolute number 3. I mean, just a 1 2 3 wala 3 hai, so matlab, like, that's why it is called 3. And maybe it is up to you. Actually, in some TCP implementation, it might also happen that that after just one or two duplicate ACKs, you detect that okay, there is a congestion, right? But generally it is 3 duplicate ACKs. Cool. So now there are two ways to detect the congestion. One is timeout and receiving the 3 duplicate ACKs. And now there are some congestion policies which is dealing with slow start and congestion avoidance. Let me go through them quickly and I will explain you very important thing. Now for next 15 minutes you are going to get something which is very nice, which is very important also. Okay, so how these two phases work? Do we need to remember these two phases? Do we need to remember some implementation? That's the whole point of this today's lecture that I wanted to deliver. I mean, this is one of the most important things that I wanted to deliver today. So let's just deal with these two phases. One is called slow start, another one is called congestion avoidance. Slow start says that since you do not know how much congestion is there in the system, so what you do? Let me just go here. Slow start. What you say that you start slowly, which means you start with some packets, and then you say that you start with sending just one packet. Since you do not know, or one segment, let me just call it segment. Since you do not know if there is a congestion or what in the in the network, you start with one segment, but it is too much pessimistic to just send one segment, right? But don't worry, once I get the ACK back, once I get the ACK back, I will be just doubling it out. Okay, I will be sending 2. Once I get the ACK, I will be sending 4. So initially I send 1, but since it is too much pessimistic, initially I send 1. Once I get the ACK, then I will be sending 2. Once I get 2 ACKs, I will be sending 4. Once I get 4 ACKs, I will be sending 8, like that, right? So it's like that. I will be sending 8. So it is slow start, but exponentially increasing. In each RTT, I am multiplying by 2. So that's called slow start, right? So slow start. Now obviously there has to be some threshold after which it has to stop, because you cannot keep on doubling, because at one time anyway you will not be getting the ACK back, and for the same region. I mean, see, one thing is that you keep on doubling, that at one time the bubble will burst up, right? I mean, you have to stop it, because you cannot keep on doubling, because after some time you will not be receiving the ACKs back. Then you have to control the congestion. Then you will be keep on reducing. So that's why there is called some threshold, which is slow start threshold, right? Slow start threshold, which we set, and we say that we will not be keep on doubling every time. We will be doubling it after for a certain limit. After that, we will be going to the congestion avoidance phase. Don't worry, I will tell you very clearly what is slow start, what is congestion avoidance, what is this threshold and all. Okay, and there is one major misconception that I will clear today regarding this slow start. Okay, this slow start threshold. One major misconception. So you send one packet, after one RTT you double it, after one more RTT you double it, after one more RTT you double it, right? So now let's see that how we are increasing this congestion window. Now there are two things that you need to understand very clearly, that you are incrementing after how much time, you are doubling after how much time. Tell me clearly. You are doubling after, so you are doubling after RTT. Now in the question, just read the question very properly, that there are two things. After every RTT you are doubling. I'm not denying it. That's not a problem. After every RTT, we double congestion window. That's not an issue. But there is one more thing here. That's true. That's not a problem here. There is one more thing, that after every ACK, see, is it after every RTT or after every ACK? See, you send this after one ACK, you are incrementing by 1. Okay. You send this after this ACK, you incremented 1. After another ACK, you incremented 1. What do I mean by that? There has been the gate question also for this particular statement. I will tell you the gate question. So after every ACK, we increment by 1. Right? Which means initially it was 1. Now let's just understand these two statements very clearly. Is this clear that after every RTT we are doubling? I think that's very easy to see. Now I will tell you after every ACK what we are doing. Okay. So after every RTT we are doubling. I hope that is clear to everyone. Now let's just see that after every RTT, after every ACK what I am doing. See here. Now after every ACK what I am doing. See, once this ACK arrives, what you are doing? Initial CWND was 1. Now, because of this one ACK, you are incrementing it by 1. That's why it is 2. Right? See, initially it was 1. Now, because of the one ACK, you are incrementing plus equal to 1. Plus equal to 1 means that whatever you had earlier, you are just incrementing by 1. Now you send 2. Now you just focus on this, or on the first red line. Okay. So maybe I can just delete other things. Okay, just see here that you send 2 packets, 2 segments, and then you receive one of them. I mean, you receive one ACK. Since you're just receiving one ACK, what you will do here, you just tell me after receiving one ACK, after receiving this ACK, what will be your congestion window? Okay, what will be your congestion window? Just tell me here. At this point in time, I'm not asking anywhere else. At this point in time, what will your congestion window? Will be, earlier it was 2, and then you will say that whatever earlier it was, you are going to increment by 1. The moment you receive this ACK, your congestion window will be 3. Right? In between it will be 3. The moment, and then you will be receiving for this next line, you will be receiving again one more again you will be receiving one more ACK, right? And then the moment you receive this, the moment you receive another ACK, your congestion window will be 3. Now at this moment, your congestion window, sorry, will be 4, equal to 3 plus 1. Let me know if you have understood this clearly. Okay. So is this clear to everyone? That's very, very important thing. So now we are going to explain congestion, TCP congestion very clearly, and you will get to understand everything very clearly, right? And there is one major misconception. I will ask you to solve one question. I'm almost sure you will do it wrongly, and then I will tell you correct. Okay. And I will give you the extended resource also. Cool. So after every ACK you're incrementing by 1, but after every RTT you are doubling it. So that's the key point that you should be knowing, right? So see here, after every RTT you are doubling it. That's not an issue, but after every ACK you are incrementing by 1 also. So that is the I mean, obviously everything I take from the extended resources. So that is I've taken from Frozen. Okay. Let me know if you have understood this. Now, what's going to happen? You are going to say that in a start it is just 1, which is 2 power 0. Now after every RTT you are going to say it is going to be like after every RTT you are going to double it. How? Basically whatever was the earlier window, whatever earlier you had, you are just going to say CWND plus that CWND. Basically, I mean, you are going to send two packets, and then you are going to increment by 2. You are going to send 4 packets. You are going to increment by 4. Why we are incrementing by 4? Because we are sending the 4 packets and we will be receiving the 4 ACKs. That's why we are incrementing by 4. Anyway, I hope you understood using this diagram, right? So after every ACK we are incrementing by 1, but after every RTT we are doubling it. So that's the difference here. Okay, cool. Now let's just understand congestion avoidance, and then we will see that how to deal with this congestion avoidance. So what does congestion avoidance says, that after the slow start there is some threshold that is called slow start threshold. Slow start threshold. So this slow start threshold is basically something which is very important. It tells you that after this point, okay, maybe it will say, let's suppose it is anything, let's suppose it is 16 mss, then you will say after 16 mss you cannot double it, okay, then you have to move to the congestion avoidance phase. And this is not any implementation dependent. I will summarize everything. I mean, whatever I am telling you is generic ideas. Okay, then I will tell you there is something which is very much implementation dependent. So there's a generic idea that after slow start you will be going to the congestion avoidance phase. In the congestion avoidance phase, in this, each time the whole window of segment is acknowledged. Whole window of segment is acknowledged. The size of the congestion window is increased by 1 only. Okay, which means whole window, for the whole window you are incrementing by 1. Okay, so basically for the whole window, okay, if the whole window initially it was 4, let's suppose, once the whole window is getting acknowledgement, you are incrementing by 1 only. Once the whole window is getting acknowledgement, you are incrementing by 1 only. So I hope you understood this. So basically after every RTT, after, I mean, basically, I mean, it's not 100% distinguish, like, I mean, what is RTT here, but I'm RTT actually should be this, okay, RTT actually should be this, but I'm assuming that there is a very less transmission delay, okay, so this delay is very less. I'm sending back to back, that's what I'm assuming. So I'm just saying that RTT here, RTT means that after like, okay, in other sense you just understand like this, after receiving the whole window, okay, after receiving whole window, we increment by 1. Now let's ask very interesting question, which is that after every ACK how much you are incrementing. This is what you are doing after whole window, but after every ACK what you are doing? After every ACK how much you are. Let me know. Okay, there is some user Aru is asking that the receiver must send ACK for the every segment, then only we say that every ACK is incremented CW by 1, but usually cumulative will be. Yeah, that's very nice doubt. Yes, that's the assumption that receiver is sending ACK for every segment. Yes, that's very nice doubt. So basically, as I said, it is implementation dependent, but here we are assuming that receiver is sending the ACK for every segment. Okay, cool. So now after every ACK, how much we are incrementing? See what is happening here, that whenever you are sending something, then after the CNW you are incrementing by 1. Okay, in every CNW we are incrementing by 1. So basically how many ACKs we receive? CW and the ACKs, right? In CW and D, which could be anything, which could be, let's suppose, 5 or something. In these many ACKs, when we receive these many ACKs, we increment by 1. We increment by 1. Now with 1 ACK we will increment, okay, this value could be anything. I'm not bothering about this value actually. So I'm not bothering about this value. So this value could be actually anything. So after 1 ACK, you increment by 1 upon C. So that's the answer here. Cool. So I hope you understood this. Now let's solve this question. But before that, okay, before I go to this question, this is a very nice question. Before that, let me just summarize everything that we have studied. So in slow start, what we do? In slow start, whenever we are sending some CWND, okay, then after receiving the whole window, we are doubling, right? We are doubling, which means that in every ACK we are actually incrementing by 1, but in slow start, In every ACK we are incrementing by 1, but here in after receiving the whole window, basically after receiving the whole window we are just incrementing by 1, which means in every ACK we are incrementing by 1 upon CWND, right? After receiving the CWND ACKs we are incrementing by 1. Okay. Now let's do this question which has been asked in GATE 2018 and which is based on the same concept that we have just talked about. So what they are saying, consider the following statements regarding the slow start phase of the TCP congestion control. Note that the CW stands for TCP congestion window and the MSS window denotes the maximum segment size. The CWND increases by 2 MSS on every successful acknowledgement. They are saying that consider the following statement regarding the slow start phase of the TCP congestion control. So they are asking about the slow start. In the slow start, CW increases by 2 on every ACK? No, by 1 only, right? CW increases by 1 on every round trip? No, on every ACK. CW approximately doubles on every round trip? Yeah, that is true. CW approximately double on every successful acknowledgement? No. Okay, that was a very nice question, I think, right? So what is the answer here? Just let me know. They're asking about the slow start. Let me know. C is answer here, which means only 4 is true. So yeah, everyone is saying 4 is true. So I hope you understood, right? They have asked about the slow start, but they may ask about the congestion avoidance also. Let me just do one thing. Let me probably just modify this question for the congestion window. Congestion avoidance. Okay. So what we can do, we can modify the same question and then we can say that here, let's talk about the congestion avoidance. Right. So instead of slow start, let me say congestion avoidance phase. CA means congestion avoidance, not the chartered accountant. Okay. So the CWND increases by 2 MSS. Let me just modify the options. Increases by 2 MSS on every ACK. Let me just say this is 1 MSS on every ACK and approximately doubles on every RTT. Okay, there is the option on approximately double side. Let me just remove it because everyone knows that it doesn't get double in congestion avoidance. Increases by 1 upon, let me just say this is 1 upon 1 upon CWND on every RTT. So yeah, anyway, there could be much options. So it increases 1 upon CWND on every RTT. This is one of the option. And let's suppose it is saying it increases 1 MSS on every ACK. So let's suppose these are the two statements, S1 and S2. So options are S1 is true, but S2 is false. Okay. B is S1 is false, but S2 is true. Both are true, both are false. What is the correct answer? Let me know what is the correct answer here. Yeah, both are false, right? So that's why C is, this D is the correct answer because this increases by 1 MSS on every ACK. No, on every RTT increases by 1 MSS. On every ACK is increases, it increases by 1 upon CWND. Right? Cool. Now let's just move further. Now, we have seen two things. One is slow start and another one is congestion avoidance. Let's not worry about that. How it happens on the RTT or how it happens on the ACK. Let's just come to one conclusion that on every RTT we are doubling on the slow start, right? Double on every RTT. This is increase by 1 on every RTT. Now, let's just see that how we are going to combine these two phases. So what we are going to do here is basically we are going to start with the slow start, and then we are going to say that let's keep on doubling till just listen here, till we get to this slow start threshold. Okay, till we get to whatever the threshold here is, and then we keep on doubling. And this is the case when there is no congestion, okay, which means there is no timeout, no through duplicate ACKs, which is very simple case. And then once you reach the threshold, you go to the congestion avoidance, and then you keep on increasing by 1 till obviously till the receiver window size. I mean, there is no point in sending more than the receiver is set, right? So that's very simple. I hope that is clear. Now let's see couple of the implementation, and we are going to see 3 implementation that what going to happen on the timeout. This is implementation 1, where I will tell you what's going to happen on the timeout and 3 duplicate ACKs, and there will be implementation 2. I think, yeah, this is the implementation 2, which is little different from the implementation 1. There is implementation 3, which is introducing one more state, which is called fast recovery, and which is also very different from implementation 1 and implementation 2. So there are 3 implementation, and they also have their names. You might have heard about TCP Reno, TCP Tahoe, I think something like this, right? Tahoe. Okay. So basically there are different names for these implementation, but good thing here is that we do not need to even know the implementation. We do not need to even know the names. What we will do, we will just check what is the common pattern among all these implementation, and there is just one thing, only just simple thing which is common, that only we think we need to remember or we need to know. And in the gate questions, then we will be solving the gate question, then you will be surprised that all of these gate question indirectly gives you the information that which implementation they are using. If they are not giving you the information that which implementation they are using, then you just imply the you just solve the questions using just one common thing which everyone is using. So there is one common thing that everyone uses, using which all of the gate questions that we are going to solve, okay, after it, all of the gate questions whatever we are going to solve, you can solve them just using the common thing that all of the implementation are using. Okay, so let's talk about the implementation 1. Right. So it is saying that you are in the slow start. Okay, you are in the slow start, and if the threshold is reaching, which means there is no congestion, threshold reaching, everything is fine. Threshold SHTH RESH SHTH RESH. So if the threshold is reaching, then you go to congestion avoidance. Very good. And that's where the life is simple. Now suppose there is some congestion, which means either 3 duplicate ACKs or timeout. Then this implementation says that whatever type of congestion it is, right, either 3 duplicate ACKs or timeout, you go to the slow start again, which means you set the CWND to 1. Either it is 3 duplicate ACKs, okay, or timeout. Similarly, even if you are in congestion avoidance, you go to the slow start, you set the CWND to 1, which means whenever there is a congestion or timeout, right? So that's the implementation 1, which says that life is very simple. Whenever you occur any 3 duplicate ACK timeouts, it does not differentiate. You go to the slow start, set the CWND to 1. Okay. Let me know if you have understood this. So learn with me is asking what is the difference between ACK and RTT. So that's a good question that he is saying what is the difference between ACK and RTT, because we get ACK in every RTT, right? Yeah, that's a good question. Let me address this question probably here. So basically he is asking that what is the difference between ACK and RTT, because we get ACK on every RTT. Yeah, can anyone answer this question? So basically here, what do I mean by RTT? RTT here I am saying that I receive the complete window. Okay, RTT here I am saying that we receive all ACKs. That's what I mean by RTT here. Okay, that's the only difference. Which means if we receive one ACK, this is just one ACK. If we receive all of the ACKs, which I'm waiting to receive two ACKs, then it is one RTT. If I'm receiving all the ACKs, then I say that okay, one RTT is complete. That's the notion that I'm using. Okay. Otherwise, if you do not comfortable with the notion, actually this is just in the standard book. That's why I'm using it. Even in the gate also they have asked using the same notion. If you're not comfortable, you can say instead of RTT, you can say whenever you receive the complete window, you double it. Okay. So instead of RTT, you can use the term complete window. Complete window. Okay. Yeah. So Siddhi is saying that RTT is for all sent. Yeah, that's just a notion that we are using. I completely agree that this notion is basically not has been used earlier. That's why there is a confusion. But in the TCP, I mean the standard books are also using the same notion. So that's why I'm also using the same notion. Yeah, that's correct. That RTT is for all sent and ACK is for the single. I mean that's just a notation. Okay. Even in the standard books, this same notation has been followed. Cool. Is this implementation one clear to everyone? That what we are doing in the implementation one? We are saying that whenever you get the congestion, either using the T3 duplicate ACK or timeout, you just go to the slow start. Then, now here I want to clear one very important thing, which is basically, suppose if there is no congestion, okay, then sorry, you basically set this congestion window by 2, not by 1. So it should be 2. I mean divided by 2 here. CWND by 2. Now let me ask you one question, and I'm almost sure that you are going to give it a wrong answer. Okay. Suppose you are in slow start, then, or maybe I can just ask you to solve one question. Okay, let's just fire one question and let's see if how many of you can answer that question. This is the question that I want to ask. Let's just solve this question. Okay, so till now you just know one thing, that if there is a congestion, you go to the slow start, right? Always go to the slow start. Let's do this question. Consider the effect of slow start on a line with 10 millisecond round trip time and no congestion is there. So RTT is given to be 10 millisecond. The receiver window size, RWND, the receiver window size is given to you, which is 24 KB, which means 12 MSS, right? How long does it take before the first full window can be sent? That's what they're asking. Let me know what is the answer. This is a question which will clarify one of the major misconceptions that you are having. Okay, most probably it will clarify. I mean, if you are having that, otherwise that's okay. This is a question where you will be getting it some misconception. So let me go to the answer. See, the receiving window size is 12 MSS, right? Now you are in the slow start, and the threshold you will set to the receiving window size by 2, which is basically 6. Now the packet goes to initially it is 1 MSS, then 2, then 4, then it cannot be 8, so you have to stop at 6. Then after 6 it will be 7, 8, 9, 10, 11. So you can count the number of RTDs, and based on that you can get the answer. Are you getting the same answer? Let me know. Yeah. So Gaurav is getting 90 and Aru is getting 80. Okay, let me know what else others are getting. Now let's see why it is misconception and what is the wrong with this solution. Actually, the solution is wrong and 90 is not the answer. This is a completely wrong solution. Can anyone tell me why this solution is wrong? why this solution is wrong. I just want to go little slow here because that's one of the major misconception that I have seen among the students. Okay, let me know very quickly that why do you think this solution is wrong so that I can move further. Aru is getting 80, Siddhi is getting 90. Okay, so these are the few answers that I'm getting, and unfortunately all of these answers are wrong. All of these answers are actually wrong. This solution itself is wrong. And what is the misconception that I want to clarify here? You just see one thing, which is that have I ever mentioned here that there is a congestion? I am saying there is a no congestion, right? I am saying there is a no congestion. Who told you to divide the threshold by 2? Who told you to set this SH, like whatever, SHTHRESH, slow start threshold to be this 12 by 2? Who said this to be 6? Who said it? See, if there is a congestion, then only you do it, right? If there is a congestion, then only you do it. Otherwise, you don't do it. If there is a congestion, then only you set it 2 by 2. That too also congestion window, not to the receiving window, right? So basically, if there is no congestion, then you just need to follow the simple approach, which means you just need to go linearly. I mean, you go here, you go in the congestion avoidance. So basically, if there is no congestion, which means you just go here after the threshold, but the threshold itself is not given to you, right? The threshold itself is not given to you. Then why you are assuming there is a threshold? So basically now understand very clearly that here I have the threshold to start with, right? SSTH, no, I mean slow start threshold. I have the threshold to start with. Then what is the initial threshold? This is called initial threshold. Initial threshold. This is called threshold. Whatever threshold I'm setting. So threshold equal to. So here I have this diagram. So sorry. Okay, I think I made, yeah. This is the threshold. I'm sorry about it. Congestion window will be 1 because we are in the slow start. So congestion window will be 1. So the threshold we are setting to congestion window divided by 2. This is the threshold that we are setting after the timeout, after the congestion. So there are two thresholds. One is the initial threshold. Another one, this is the threshold after congestion. So this threshold after congestion is very easy to find out, right? Threshold after congestion is very easy to find out. How? Because I just need to divide by 2. That's the threshold after congestion. But this initial threshold, how to find out this initial threshold? That has to be given in the question actually. You cannot find it out, okay? That has to be given in the question. So basically this initial threshold has to be given. That is basically the pre-agreed value. See, I have taken this the screenshots from the Frozen. That's why I'm saying this is misconception, and I always clarify the misconception using the standard resources link so that you get to trust more, okay? So see here, they are saying that threshold variable to be a pre-agreed value, normally a multiple of MSS and CWND to 1 MSS. So basically this is the initial threshold. But if you are reaching to the congestion, then it is divided by 2, right? See here that TCP immediately interrupts this aggressive growth and restart a new, if the congestion is detected. If the congestion is detected, then you limit it, you limit the threshold to half of the current congestion window, not even the receiver window, okay? So the initial threshold, that should be the pre-agreed value. That's what I want to convey. If it is not given, you cannot limit yourself to, if there is no congestion, then why you are running? You just send it twice. Always double the window size, right? If there is no congestion, if there is no threshold and there is no congestion, always double it twice. So Utsav is getting 40 millisecond and the 40 millisecond is the correct answer. Right? Okay. Someone is, Siddhi is asking the question. So this is the question. So here in this question, I am given that RTT is this, receiver window size is 12 MSS, and then I have asked that how many RTTs it will take. Now what people are doing, people are starting with 1, right? The initial MSS is like starting with slow start. They are saying that slow start threshold is basically 6 MSS. They are saying this, which is first of all wrong, right? Because you do not divide the receiver window, you divide the congestion window, that too after the congestion. But it is clearly written there is no congestion. Then why you are setting the initial threshold? This is the initial threshold, right? So initial threshold, if it is not given, because there is no congestion, you do not need the threshold. You just double it, right? So it is 1, then it is 2, then it is 4, then it is 8, then you want to set 12, then it is 12. So from initially it is 1, then you get 2, right? So it will be 1 RTT from 1 to 2. So it is 1 RTT, 2 RTT, 3 RTT, 4 RTT. Since it is 4 RTTs, you will be taking 4 into 10, which is 40 milliseconds. So only Utsav has got this correct answer. Let me know if everyone is clear about this concept. So the concept here is that you do not need to set the initial threshold. Okay, so Utsav has got the correct answer, and maybe he have used the correct concept. So basically the correct concept is that the initial threshold, if it is not given, you cannot limit yourself to some initial threshold. That to receiver window divide by 2. Who has told you to divide the receiver window, right? We always divide the congestion window first of all, right, by 2. And if that too there is a congestion, if there is no congestion, then why you are limiting yourself to send the more packet? Why after the 4 or you want to send 6 and then 7, 8, 9, 10, 11? No, right? And this question I have taken from Standard University, which is this university, and there is a solution here which is 14 milliseconds, right? Okay, let me know if you have understood this clearly. So this is a major misconception that I have observed among the students. So that's why I said this is one of the misconceptions. I will clarify 2-3 more points today. Okay, let's just continue the session. Now there is another implementation. So I hope you understood this particular question. This particular question was very easy if you know the concept, right? And we have seen one of the implementation which is basically saying that you always go to the slow start whenever there is a congestion. So let me write one of the implementation. Always go to slow start whenever there is a okay. Congestion means timeout or reduplicate. Good. Now let's take one example probably, and for this implementation one, and then you will maybe get to understand more. Okay, so let's take one example. Suppose that I start, okay, and like I mean I'm following the implementation one, and let's suppose that I start with slow start 1. I mean in the slow start phase, and initially I have 1 MSS. Then I send a packet, and then I do the congestion window to be 3 MSS. Sorry, 2 MSS. And then again I'm in just a slow start. So from 2 I will go to 4. Then from 4 I will go to 8, right? So because I'm in the slow start. So from 2 to 4, 4 to 8. Now suppose at this point in time I'm getting some congestion. Okay, suppose I'm getting some congestion, and the congestion is because of the timeout here, right? Whenever I got the 8, now suppose I get some congestion because of timeout. Then what will I do? Tell me. What will be the new congestion window? New congestion window will be 1, and then I will again start with the 1, right? And I keep on just doubling it because I'm in the slow start, but till the threshold. So I will say the congestion window is 1, but my threshold, right, slow start threshold is now 4. So I will go from 1 to 2 to 4, right? And let's say that I keep on continuing, which means now I will go to the congestion avoidance phase. In the congestion avoidance phase, I will be just incrementing linearly. So from 4 I will be incrementing to 5. Why I went to congestion avoidance phase? Because this is the slow start threshold, right? So for 4, 5, and let's suppose I keep on doing it, and I do it couple of times, maybe 5, 6, 7, 8, 9, 10, 11, 12, like that, right? Suppose I do it couple of times. So basically, I start with 1. I'm in the slow start. This portion is the slow start. This is the slow start. In the slow start, I got the congestion. Whatever could be the reason for this particular implementation, it does not depend. But the congestion is, let's suppose, because of timeout. Then I set the congestion window to 1, and the threshold to be 4. Then 1, 2, 4, and then this is basically again congestion avoidance, and this is again the slow start. So from slow start, I'm going to slow start. Now let's suppose that I again get the congestion here, and this time the congestion is because of 3 duplicate ACKs. Now, in this case, what will I do? Can anyone tell me? If I'm getting congestion because of 3 duplicate ACKs, then what will I do? Actually, I do not care. I always go to the slow start. That's the implementation stage basically, right? I will go to the slow start and I will set the threshold value to be, this time it will be 6, right? I mean, earlier it was 4. Now this time it will be 6. And I will again go to the slow start. Let me know if that is clear to everyone. Right? Now, from the slow start, I will be incrementing it. I mean, I will be doubling it. 1 to 2, 2 to 4. But 4 to 8 I cannot go, so I will just go to 6. I will limit myself. Then 6 to 7, and then like I will be doing it continuously. Let's suppose 6 to 7 to 8, 9, and then 10 I do. So this is the whole, this is I keep on doing it, and till I get either congestion or this size is same as the receiver window size. So basically, I hope you understood that whenever there is a congestion, maybe because of the timeout or because of the 3 duplicate ACKs, I do not care. I always go to the slow start. That's the only point I want to convey here. This is the implementation one. Right? See, this diagram is telling you the same thing. So here I have the diagram, which is telling you the same thing. Whenever you have the congestion there, because of the timeout or because of the 3 duplicate ACKs, whenever you have the congestion, you immediately drop down it to 1 and you start your slow start, right? You immediately drop down to 1. But now let's the implementation 2, which actually differentiate between timeout and 3 duplicate ACKs. It says that in case of 3 duplicate ACKs, you do not go to the slow start. You can go to the congestion avoidance phase. Or that's the only difference. Okay, let me just show you. So implementation 2 says you are having slow start, you are having congestion avoidance, that is fine. So whenever there is a congestion, you will ask whether it is because of 3 duplicate ACKs. If it is because of 3 duplicate ACKs, you always go to the congestion avoidance. Now you increment linearly and you set your congestion window to half of the earlier window and threshold to the half of the earlier window, like that, right? Which is the slow start threshold. Actually, this threshold won't matter much because you are not in the slow start phase. I mean, currently it will not matter much because you are not even in the slow start phase. So why it will matter, right? Okay. So if there is a 3 ACKs, you go to the congestion avoidance. But if there is a timeout, then you will go to the slow start. If there is a timeout, you go to the slow start. So let's just take one example and let's just see how it is happening. So see here, like this is just a picture, and then I will tell you one numeric example also. So here you start with initial window, which is 1, and then this is the window. Okay, this is the congestion window. This is the RTTs. So you keep on doubling it. Let's suppose at some time after once it becomes 16, then you reach the threshold. Then I mean, this should be the initial threshold. Okay, that you pre-agreed value, because there is no congestion. So this should be some pre-agreed value, and then I linearly incrementing it. Then I reach to the congestion. Now if it is timeout, I go to the slow start. Then I do the same thing. If it is let's suppose this is the 3 duplicate ACKs, then I go to the congestion avoidance phase. That's the only difference, right? So let me know if that is clear. Now if that is clear, let's just see some example, and then we will see the implementation 3. So let's just say that I start with 1 and there is an initial threshold that is given to me. Okay. Let's suppose 16, some initial threshold is given to me. So what will I do? I will start with 1 and then I will say it is 2, this is 4, this is 8, then 16, right? Now since I reach the initial threshold, I will be incrementing with linearly 17 till like that I will be incrementing, and let's suppose after maybe 20 I get the congestion. 17, 18, 19, 20, and then there is a congestion. Okay, so suppose there is a congestion here. I deducted the congestion, and that is because of timeout, because of the timeout. So what will I do? Since it is because of timeout, then I will set my threshold to be 10. I will go to the slow start, and again 1, like that, right? So I will be keep on incrementing it. I mean, keep on doubling it. 1, 2, 4, 8, and then 10. So this is the slow start. Then I will say that okay, now my slow start is completed. Now I will go to the congestion avoidance, because this 10 is meeting the threshold. So which means 11, like that, right? So it will be, like I will be keep on incrementing it, and like after till I get the congestion. So basically I will be keep on incrementing it, 11, 12, something like this, right? So let's suppose this is 11, 12, and linearly I will be incrementing, and then let's suppose I again get the congestion, but now this time because of the 3 AC case. If I'm getting because of the 3 AC case, then I will go to the slow start. Sorry, I will go to the congestion avoidance. I will set it to 6, although it does not matter, but yeah, I will go to the slow start. So by the congestion window, which will be half of it. So that's the only difference. So here I will be starting with 6. That's the only difference, right? So 6, and then this is the congestion avoidance. So it will be 6, 7, 8, like that I will be keep on doing. Let me know if you have understood this. So what is the difference between earlier and this? Earlier at this point, whenever I got 3 duplicate AC gauge, I started with 1, but here I will be going to the congestion avoidance phase, which means I will start with 6, 7, 8. That's the only difference. Okay. Now if you have understood this, then let me know, do you see any similarity between two implementations? See, on 3 duplicate AC case, both are different, but on the timeout, both are same. On the timeout, both behaviors are same. That's the key takeaway here, right? On the timeout, both are going to the slow start, isn't it? So on the timeout, both implementation, you do not need to know which one is Reno, which one is how. You do not need to know all of this, okay? So on the timeout, both implementation go to slow start. That's the key takeaway actually. Okay. Now, if you have understood this, then let's just go to the implementation 3, which is actually a latest implementation. But fortunately, you do not need to remember this implementation, and this is very complicated implementation. I'm almost sure that this implementation you have not studied till now. Okay, from wherever you have studied, if you have not studied from the standard resource, then you have not studied till now. Good news is that you do not need to study it. Okay, this is just a one diagram that I'm just telling you. I will not even go through this diagram. There is one more state which is called fast recovery or something, and they actually use some threshold +3 or something like that. That's, I think, very latest, and this is the implementation that TCP Reno is using. Okay, I'm not sure it is Reno or Tahao, but I think Reno. Anyway, so this implementation also has one thing common with the earlier implementation, which is again the timeout. See, if you observe on 3 duplicate AC case, I'm introducing a new state which is fast recovery or something. But on the timeout, whenever the timeout is here, okay, timeout. If there is a timeout, if in this state, if there is a timeout, this state there is a timeout, in this state there is a timeout. Whenever there is a timeout, I'm always going to the slow start. So that's the only thing I need to remember. In any implementation you talk about in TCP, you always go to the slow start in timeout. So Sumant is asking, when we are in the slow start, if we get 3 AC cage, then we go to the congestion avoidance in the implementation 2. So he is saying that if we are in the slow start, we get the 3 duplicate AC cage. Yes, you always go to the congestion avoidance in case of 3 duplicate AC cage. Fortunately, what you are doing in the 3 duplicate AC cage, you do not need to remember. They will tell you, because on the 3 duplicate AC case, the things are differing in every implementation. So you do not need to remember what is happening at the 3 duplicate AC case. See, at the 3 duplicate AC case, here the things are very complicated. You are incrementing it by +3, and I mean you are introducing one more state, fast recovery or something. So the key takeaway here is that on the timeout, both implementation, or not just a both implementation, all the implementation basically, right? All the implementations all implementations go to slow start on 3 duplicate ACKs. Who cares? I mean, don't remember it, right? So don't remember that what's going to happen on the 3 duplicate ACKs will be given in the question. Will be given in the question. So that's the very, very important takeaway, that people are getting actually confused. I have seen many students who are getting confused, sir, on 3 duplicate ACKs, what to do, which RFC to follow. They even talked about RFC and all. Dude, Gate will not ask you to remember those RFCs documentations, right? I mean, what's the point in remembering the whole documentation? Will Gate ever ask you to remember the documentation? I don't think, right? Since there are implementation dependent, Gate never asks something which is implementation dependent. By chance, if Gate asks, that is once in like 40 years, 50 years, then it is okay. I mean, that's fine. I don't think they can ever ask, but if they give you, okay, according to this RFC, according to this implementation, I don't think they are like, this is my intuition, they will never ask you to remember any documentation, right? So don't worry what is happening in the 3 duplicate ACKs, which implementation to remember, which not to remember, which RFC to remember. No. Like I was talking to one of the student, he told me that, sir, I even gone through the documentation. I have seen one of the YouTube video here, like people are talking about that, okay, you need to study the RFC and all based on this RFC and whatever. Okay, so like this is happening. So like from that only I got to know that there is some some chaos that we need to basically filter out. We need to make it clear that what you should do, what you should not do. Okay. So I hope you understood that you only need to know that on timeout, go to select start, and on 3 duplicate ACKs, don't remember. Okay. So that's the only thing that you need to remember, that what you are doing on the timeout, not on the 3 duplicate ACK. Let me know if that is clear to everyone. On 3 duplicate ACKs, implementation dependent. Okay. Now the question is, will Gate ask you that what's going to happen on the 3 duplicate ACKs? Answer is no, because it is implementation dependent. If they have to ask you, they will give you that, okay, this is the thing that is going to happen on the 3 duplicate ACKs. If any test series is having that kind of question, that they assume any implementation by their choice, then just don't follow that test series. Whenever I in the go classes or Arjun sir in the GATEOverflow, whenever we give the question in the test series, either we mention that what is happening, we mention the complete detail that on 3 duplicate ACKs what to do, on timeout what to do, or otherwise we do not ask about the 3 duplicate ACKs. We only ask about the timeout, because Gate only ask about the timeout. Let me just show you. See, this is the question that Gate has asked. Now here they are saying, assume that timeout occurs. Okay, assume that timeout occurs. They are not asking about the 3 duplicate ACKs. Let me go to the next question. Now here they see when a timeout occurs. Now again they are saying timeout occurs. They are not asking about the 3 duplicate ACKs because it is implementation dependent, right? Now let's go to another question. See, okay, this is not related to that particular concept. Let me go to another question. Okay, see here in this particular question, do you remember the question that I talked about, major misconception? Major misconception, right? Where the people were doing SSTH, slow start threshold to be RWND by 2. This question is based on the same misconception, very recent question that they've asked in 2020. Based on the same misconception, here also they are saying, assume that no timeout and errors during the transmission, there is no congestion. If there is no congestion, do not fall in the trap of this. Okay, You just keep on doubling if there is no congestion. We will solve this question, don't worry. Okay, but I'm just telling you upfront, they are saying there is no congestion. This is same as the question that we have just solved, which I talked about, which is major misconception, right? Okay, so this is the misconception that in case of no congestion also people do it. Let me know if things are clear to everyone. Now, okay, I do not have much question because only these are the questions that Gate have asked, or whenever Gate asks, they will always give you that this is the timeout. They can never give you 3 duplicate AC gates. Let me know if this is clear or there is still any confusion. Then we will directly solve the Gate PYQs so that we get the more understanding. Then we will go to the one of the another topic, which is timers, TCP timers. Okay. Just confirm me quickly that you have understood everything. If you have understood, just let me know. If there is any doubt, just let me know. Okay. So Sumant, Gaurav, Ussab, Siddhi, Aru, learn with me, Sukesh, Sumant. Everyone understood this clearly? Lalit? Okay. Now let's solve some questions, right? Do you think there should be a 5 or 10 minutes break? Let me know. So let's maybe meet at 12:50. Let's have a small quick break. Let's meet at 12:50 and then we will be continuing with the questions. So after this, what we need to do? We need to basically understand this concept more clearly using the help of questions, and then you will get to understand the TCP congestion very clearly, right? I told you that's very easy concept, right? This is the only concept in TCP congestion. The only concept in TCP congestion, only one concept, right? So let me just write it here. Okay, there is only one concept, only one concept. That's all. And on timeout, go to the slow start. Good. So now let's meet at 12:50. Hi everyone. Let me know if I'm audible. Okay. So let's solve some questions. Maybe you will get to know more. So TCP and network layer both are actually very easy. And put this TCP network layer and these combinedly, then I will say that computer networks itself is very easy, right? I mean, it is not very easy, but it is not tough at the same time if you know the basics. Okay. Let's do this question. Consider an instance of TCP additive increase multiple decrease algorithm where the window size at the start of slow start, so they are saying 2 MSS with 2 MSS they are starting, and the slow start at the and the threshold at the start of the first transmission. See, what is this threshold? Can anybody tell me? This is the initial threshold. Whenever they give the at the start of the first transmission any threshold or something, this is the initial threshold. So it means the slow start threshold to start with, they have given to be 8 MSS. Now assume that timeout occurs during the 5th transmission. Okay, then find the congestion window size at the end of 10th transmission. So there is a timeout. See, again there is a timeout, right? Cool. Let's start. So 2, then from 2, what you will do, since you are in slow start, you will go to 4, 4 to 8. But you have reached the threshold, you will say that now you will go linearly. So this is the first transmission, second transmission, third transmission, fourth transmission, and during the 5th transmission, the timeout has occurred. I mean, there is a congestion, and congestion is because of the timeout. So you are sending 10 packets, and then you got the congestion, right? Now, let me know if you if you are getting the things, if it is clear till this point, right? So what we are saying that there is a timeout whenever you are sending 10. Okay. So now let's just continue. Now they are saying, because this is the fifth transmission. Now it means that they are saying this in their timeout. You will set it to be the initial threshold, the threshold to be 5. Then you will go to the slow start. You will say, okay, this is 1. Then this is 2. This is 3. Then 4. And what they are saying, find the congestion window at the end of 10th transmission. This is the end of the first transmission. Second, third, fourth, fifth, sixth, 7, 8, 9, and this is 5. Is this correct? Sorry, we are going to the slow start, right? So this is 1, then you will go to 2, then you go to 4, and then you go to 5, right? Because slow start is 5. So I mean, you go to 1, 2, 4, 5, and then you will go to, from this 5 you will go to 6. So basically this is end of first, second, third, fourth, fifth, sixth, 7, 8, 9, 10. So at the end of 10th you are having 6, right? I mean, at the end of 10th you just finish transmitting 10, and then you are having 6 as your congestion window size. So 6 is not in the options, right? See, this is the end of the first transmission. This is the end of the second transmission, because at the end, I mean, you start transmitting, you, okay, end of the transmission means what? I think end of the transmission means that whenever you're sending something, this is the start of the transmission, and end they mean by end this. We call this is a one transmission. Okay, this is one transmission. Whenever we say that, okay, this has been received successfully, we say this is a one transmission. So end of transmission means that you receive the AC cage also, right? So which means that you receive the AC cage also. So here this is the this is the end of the first transmission and the start of the second. So basically 1, 2, 3, 4, 5, 6, 7, this is 10, which means that you just you have sent the 6 during the 10th transmission, you have sent the 6, but when you receive all of the AC cage, then you will say that this is the end of the 10th transmission, and your answer will be 7. You're getting my point, what I'm saying here? See, what is the transmission? The transmission is that you end sending, I mean, you have received the AC gauge also, that's called the transmission, right? So what we are saying, that end of the 10th transmission, so you are sending six packets, you are sending 6 segments in 10th transmission, so basically you are sending six segments in 10th transmission, which means whenever you are sending the 6 packet, okay, so this is 1, 2, 3, 4, 5, 6, this is the 10th transmission. But what is the end of the 10th transmission? When you receive all of the ACK, this is called end of the transmission, right? So at this moment they are asking, so it should be 7. But here there is a problem that they are saying you are starting the slow start with 2. So should we do the slow start threshold whenever you are moving to the slow start? It should be 1 or it should be 2. So that's the confusion here, right? I mean, should it be 1 or 2? So that's why during this question they have given marks to all basically. See, they have given there's an ambiguity here that if the window size will be 1 or 2 whenever you are going to the slow start. Due to this reason, gave marks to all. Assuming the window size to be 1 MSS, then you can solve like that, right? So anyway, the important point here is to understand that what they mean by end of the some transmission. End of transmission mean this is whatever you are sending, this is the start of the transmission. When you receive all the ACKs, this is called end of the transmission. This is the transmission completion. Okay, here you complete the transmission. Complete the transmission. That's what important point here is to understand. Rather than just directly solving without even understanding what is the transmission, then it does not make sense to solve this question, right? I hope you understood. Now let's move to the next question. This is the next question, and what they're asking here is that let the size of the congestion window in the TCP is 32 kb. So they are saying congestion window size is 32 kb. When a timeout occurs, see the timeout they are saying, when a timeout occurs, the round trip time of the congestion of the connection is 100 milliseconds. So RTT is also given to you, which is 100 milliseconds. The maximum segment size used is 2 kb. So maximum segment size they are saying is 2 kb. Okay, which means congestion window is 16 MSS. The time taken by the TCP connection to get back this 16 MSS congestion window. So they are saying that the TCP connection is this much, and when the timeout occurs, so there is a timeout. I mean, they just got the timeout, and at this time you have the congestion window this, which means you will set your threshold to be 8, and since it is timeout, you will starting with the slow start. You will say this is 1, this is 2, this is 4, this is 8, and then you reach the threshold. Then you will say this is 9. Right after that, you will say this is 9, 10. And this is I mean, they are asking that how long you will be getting 16, 9, 10, 11, 12, 13, 15, 16. So how many RTTs do you have till 16? This is 1, 2, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 RTTs. Let me see the answer. Okay, there are 11 RTTs. This is 2, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They are having 2, 4, 8, 16. This is 1, 2, 4, 8. Yeah, 2, 4, 6, 2, 4, 8, 16, 18, 20, 22. Where I missing? 1, 2, 4, 5, 6, 7, 8, 9, 10. Okay, so I'm missing one count. I don't know how. This you are starting with 1, then go to 2, then 4, then 8, and then since you reach the threshold, then you will go to 9, 10, 11. Okay, 14, number 14 is missing here. Cool. So number 14 was missing. So that's why the total is 11. So RTTs that you are taking is 11, and you can solve this question. RTT 11 RTT means 11 into 100 milliseconds, right? So it means 1100 milliseconds. Okay, cool. Now let's just continue, right? I hope you understood this question. Let's just continue with this question. Let me know what answer you are getting for this question. On a TCP connection, current congestion window size is this much. The window size advertised by the receiver, okay, they are saying the congestion window is 4 kb. Window size advertised by the receiver is basically 6 kb. The last byte sent by the sender, last byte sent is 1024. So sender has just finished sending. You don't know the start byte, but you know the last byte, which means the ACK will be 1024 plus 1 basically. I mean, okay, last byte is 102440. So in the sender window, you will say you just finishing this side, this byte, which is basically 102440, 240, 0240. Okay. and then this is how your sender window looks like. I mean, you have sent all of the bytes from the initial sequence number till 10240 byte number, right? Now you are ready to send the next byte. The last byte acknowledged by the receiver is 8192. Okay, so which means that you have sent this much byte and receiver is saying you need 8192. So basically, this is the receiver, receiver has acknowledged, which means before that things are not acknowledged. I'm so sorry, things has been received, and now the receiver is saying that I am expecting 4192, right? So receiver is saying that I am expecting 8192, right? The receiver has said I am expecting 8192. So the sender must have sent till now, okay, maybe in one packet, maybe in multiple packets, that I don't know, but yeah, sender must have sent 8192, this sequence number, and last byte sent is also given, which is 10240, right? I mean, sender just sent 8192 because receiver is asking for 8192. Sender is sending this as a last byte, so sender must have sent this in maybe one MSS in multiple segments, that I don't know, but yeah, segment this much in the transit, right? This data in the transit. Transit means it is still in air. Now what they are asking, the current window size at the sender. So what is the current window size at the sender? Since it has not got the acknowledgement of this, then you will say how much byte it is. Let me know what is the answer you are getting. See, the congestion window given to us, advertise window also given to us. I mean, whatever they are advertising, this is also given to us, right? So maybe let me go to the next page. Then they are saying that congestion window and advertise window both are given to us, which is congestion window is 4 kb and receiver is advertising to be 6 kb. Now obviously the sender window will be minimum of both of this, right? Minimum of both of this, which is sender window will be minimum of 4 or 6, that will be 4 kb, right? Because I know the congestion window, I know the receiver window, so sender window will be 4 kb. Let me know if that is clear. But let's just understand this question more carefully. So here, how does it look like in the sending window size? So basically 4 kb means it is 4 into 1024, which will be 4096 bytes. 96 bytes. So this is your sender window size, right? Now let's just see that how does the buffer look like. Now they are saying that the receiver has acknowledgement last byte is 8192. I mean, the receiver has acknowledged this byte, which means that the sender is saying that till 8192 it is received. Now let's just divide it into two parts. They are saying that I just got the acknowledgement for 8192 basically, right? This has been acknowledged. Now I have not got acknowledged for this byte, right, which is basically 8193. This is the byte number 8193. For that I have not got acknowledgement. Okay, earlier I think I written 8192, but it should be 8193 because 8192 acknowledgement has been received, right? So that's why it should be 8193. So I have not received the acknowledgement for this, and I have also sent, they are saying I have also sent how many bytes? I have just sent the byte which is last byte is 1024240, right? So how many bytes this is? Can anyone tell me how many bytes are in the transit? So let me just calculate number of bytes in the air, right? I mean, sender window size is okay, that's easy to calculate, but let's just focus on this question little more carefully. So tell me how many bytes are in the transit. This is 10240 minus 8193 plus 1, right? Should be plus 1. So what it should be? What you are getting? Let me just see. 10240 minus 819. We do, so 2048 you are getting, right? 2048. So basically these many bytes you have sent, these many bytes are in transit, which means sent but not acknowledged, not acknowledged are 2048 bytes, right? And the total window size is 4096, which means that double of this, which means this is also 2048. So basically what is happening now, that now let's not play with the byte number, let me just play with the let me just tell you with the window size. So basically these are 2048 bytes, these are also 2048 bytes. I mean, this is the sender window. So basically the sender window, complete sender window is 4096. Out of this, you have sent it, you have received it. So this is acknowledged act, and this is sent but not act. Right? This is the current sender window situation. Let me know if that is clear. Okay. I mean, this is the complete picture, what is happening in the sender window size. Now, this must be the situation for, I mean, what must have happened before it. So basically, this is to reach this situation, what must have happened. Receiver must have said that, see, just send me, okay, how much it has advertised, 6 KB, but the congestion window is 4 KB. Receiver is saying, send me 6 KB. I can, I mean, I can handle till 6 KB. But since I know at the center side, the congestion window also I calculate that happens to be 4 KB. So I can send at most 4 KB. So sender has sent 4 KB. Sent, right? So sender has sent 4 KB because of the congestion window. Now this 4 KB might be part of multiple MSS. Okay, this is maybe in 10 MSS or whatever, right? Depends on the MSS size, in multiple MSS basically. In multiple MSS. Now receiver has acknowledged this, okay? Receiver has acknowledged this, but not all 4 KB, maybe half of it. So receiver is saying that half of this I have received and maybe half of this is in the transit, okay? You don't know, maybe lost or maybe in the transit. So receiver, this is at the center side, you actually send the 4 KB, right? This is your window, you actually send the 4 KB, and then you are saying that this has been acknowledged, this is not yet acknowledged. Now, since the receiver is going to send the acknowledgement, at that time receiver will again tell, okay, receiver will again tell the receiving window size. Now, based on this, see, these are the 2048 bytes. Now let's suppose receiver is again saying, maybe let's suppose it is saying that 2048 into 4. Okay, these many bytes. Let's suppose this is receiving window, whatever. Okay, I mean receiver will again advertise the receiving window. Based on that, I will just expand. I will just expand. I mean, I will just expand or shrink my sender window based on the whatever receiver is again advertising. So anyway, let's not worry about what receiver is again advertising. But yeah, whenever it is sending the ACK, it will again tell the receiving window size, right? So this must have happened. I mean, receiver must have said like send me 6 KB, because of the congestion I am sending 4 KB. Then out of this 4 KB, half of them has been acknowledged, half of them has been not acknowledged. That's the situation that we are getting. Cool. So this question can be solved easily by taking the minimum, but that's not the interest. I mean, the question you can solve, but if you want to understand what they are saying, then you should be actually doing it. I mean, you should be saying, you should be actually, I mean, doing a little more analysis on the question. Cool. Let's do this question. This question has been asked in GO 2016. They are saying identify the correct sequence in which the following packets are transmitted on the network by the host when a browser requests a web page from a remote server. So whenever you are requesting a page or something, first you need to know the DNS, right? I mean, you have to put the DNS query to the DNS server. Once you know the IP address, okay, you know the IP address, then you establish a TCP connection. Okay, that's the first step. After you know the IP address, TCP connection. Once you establish the TCP connection, then only you do other things, which means you use the HTTP or whatever you want to use. So DNS, TCP and HTTP should be the answer. So that's why C is the correct answer. C is the correct answer. DNS, TCP and HTTP. Cool. Let's do this question. This question has been asked in GATE 2020 and this is a good question. Let's do it. So what they are saying, they are asking They're saying that consider a TCP connection between a client and a server with the following specification. The round trip time is 6 millisecond, which means for the TCP, the round trip time is 6 milliseconds. So let me just write it. RTT is equal to 6 milliseconds. The size of the receiver advertising window, so RWND, is basically 50 KB. The slow start threshold, okay, see here, they have given the slow start threshold at the initial. So it is actually initial slow start threshold, right? So slow start threshold also given here, which is 32 KB. And the maximum segment size is 2 KB. So maximum segment size 2 KB means this is 25 MSS, 16 MSS. So see here that the slow start threshold is given explicitly, okay, which means it must be the initial slow start threshold, because after the congestion anyway we will do the half of it. The connection is established at t equal to 0, okay, which means you do not need to take care about the connection establishment. I mean, connection has been already established. Now you are starting your timer, okay, at t equal to 0. So connection must have been already established, but I'm saying connection has been established and now we are starting our timer, which is t equal to 0. Assume that there is no timeouts and the error during the transmission. So they are saying there is no error or timeout during the transmission. The size of the congestion window at the time t plus 60 millisecond. T plus 60 means RTT 6 millisecond means that after 10 RTTs, right? Okay, let's just see. So see here, initially what is, initially you will be in the slow start, right? Let me just, yeah, slow start threshold is given. So initially you are in the slow start, which is basically 1, and then the threshold is 16, so you will keep on incrementing 1, 2, 4, 8 and 16. Now tell me, after the 16 what you will be doing? Have you reached your slow start threshold? Answer is yes, right? Since you have reached your slow start threshold, that's why after the 16 you will be going to 17. You need to go to 25, right? So what they are asking at time t plus 60, okay. So 17, 18, 19, 20, 21, like that. You will be keep on going 22, 23, 24, 25, like that, right? Okay. Now let's just see that how many RTTs I'm taking from here. So this is at t equal to 0. Now after receiving, okay, after receiving one set of all ACKs here, we are saying it 1 RTT, which means this is 1 RTT, and this 2 is basically after 6 seconds, 6 milliseconds. After 1 RTT has been crossed, then I am having the congestion window as 2, right? Now another RTT, 2 RTTs, then congestion window is 4, then 3 RTTs, 4 RTTs, 5 RTTs, 6, 7, 8, 9, 10. So after 10 RTTs, I will be having 22 as my 22 as my congestion window. So what they are asking, the size of the congestion window they are asking. So 22 means that they have given the segment size is 2 KB. So it means 22 I will be having after 10 RTTs. So 22 MSS means 44 KB. In the KBs they are asking, so it should be in KB, which should be 44. Very easy question, right? Since there is no congestion, so you do not need to worry about it. I mean, they have given the initial threshold, but by chance they do not give you initial threshold, then if they do not even give you the initial threshold, then it means that you should not limit yourself. You just keep on incrementing. After 16, you directly go to 32, but you cannot go to 32 because of the receiving window size is just 25 MSS. So you will, after 16 only, you will directly go to 25. Okay. I hope you understood this. Now let's talk about very small topic, which is TCP timer. So TCP manages few of the timer, and at least 5 of the timers are all, like in all the implementation they manage 5 of the timers. There might be more in other implementation, but at least 5 you manage. One is retransmission timer, another one is persistent timer, keep alive, time wait, ACK timer. So these are the timers that we have. Let's first understand retransmission timer, and then we will keep on understanding every other timer. So these are the timers you have. Then let's start with retransmission timer. So whenever you are sending some packet, right, then this is a timer that is called retransmission timeout, RTO. This is a timer after which, if I I will wait for the ACK. If I get the ACK, it is fine. But if I do not wait for the ACK, if I do not get the ACK, then after this timer, which is called RTO, retransmission timeout, after this timer, I will send again the packet, right? Send packet again. That is called retransmission timeout. See, when TCP sends a segment, it creates a retransmission timeout to that segment. If an acknowledgement is received before that, then it is good, timer is destroyed. If timer goes off before the acknowledgement arrives, then we will retransmit it and reset the timer, right? Which means if I'm sending something, if I do not get the ACK within the timer, this is RTO. If I do not get the ACK, then I will retransmit it. That's called RTO. Very easy. Okay, let me know if there is any problem in understanding. Now let's go to another timer, which is persistent timer. We will come back to this retransmission timer, that how to calculate it. Okay, how to calculate the retransmission timer, we will come back to this in just a minute. I mean, once I finish all of the definition, then I will again come back to this retransmission again. Okay, because there are ways to calculate it, and for other timers it is just a definition. So for the retransmission I will come back. Now let's go to the persistent timer. Now the persistent timer says that, let's suppose you have there is a sender receiver communication that is happening. The receiver sends an acknowledgement with the window size of 0, which means receiver is saying that, see, my window is full. Receiver is saying that my window is full because of some reason, maybe genuinely full, or maybe you are using the Clark solution that I told you. But anyway, the receiver is saying my window is full. The sender will say that, okay, good, like let me just wait. I will be waiting, right? The sender will say, okay, I will wait till you give me RW, right? RWND. You advertise me RWND again. Then after some time, the receiver is saying that, okay, see, my window is not full. Now I can expect maybe I can accept, maybe let's suppose some MSS, or maybe let's suppose 30 MSS, okay, or maybe some KB. It is saying that now I can accept some of the bytes. But unfortunately, this packet is getting lost, right? Now this is a deadlock situation where the sender will think that receiver is still 0. Receiver will think that sender do not have any data to send, because I have just sent some ACK. Okay, it might be the pure ACK, right? It might be the pure ACK, and it is saying that that I'm expecting 30 MSS. So receiver knows that since I have just sent the pure ACK, then it will not expect the ACK again for the ACK, obviously. So receiver does not know that what is the reason that it is waiting. Maybe the packet is lost, or the sender does not have data to send, right? So basically, you advertise the receiver window to be 0, and then you again advertise to some non-zero number, but this time the packet is lost. So what do you do? This is a deadlock situation, because sender will think that receiver still have receiver window 0. Receiver will think that sender do not have any data to send. So to resolve this situation, we have or the sender have one timer, which is the persistent timer, right? So persistent timer is some timer. Whenever this advertised to 0, it will start persistent timer here. Start persistent timer here. It will say that, okay, after some time I will again ask, are you still 0? Which means that if you are advertising me to be that receiver window size is 0, okay, if you are saying me that receiver window size is 0, then I will start the persistent timer here, right? I will start a persistent timer, and after some timer I will again ask, are you still 0? Like that, right? So that's all. That's called persistent timer. I hope you understood. Now another term is basically there. Another timer is keep alive timer. Keep alive timer is, as the name suggests, it is also very easy. It says when a connection has been idle for a long time, the keep alive timer may go off to cause one side to check whether the other is still there. Which means that, let's suppose there is a sender, there is a receiver, and this sender is sending something. Receiver is acknowledging that it has received, right? Let's suppose this happened. Now sender is not saying that I want to terminate the connection, neither it is sending something, right? So receiver does not know that what to do. I mean, whether the sender is still there, it does not have any data to send, or it has been actually died off, right? So receiver will say, are you alive? Or maybe sender can also say, I mean, any party can ask, are you alive? Using the keep alive timer. Basically, after some time, whenever after some communication, let's suppose this communication is happening, then after this packet has been received, it start the keep alive timer. It will just ask whether you are still alive or not, right? So see here, when a connection has been idle for a long time, the keep alive timer may go off to cause one side to check whether the connection is still alive. Very normal definitions, just you need to know the definition. Okay, now there is one more timer which is called time wait timer. Time wait timer is little interesting. It says whenever you are closing the connection, okay, I think I have that diagram with me. Yeah, so whenever you are sending the fin, I mean someone is sending the fin, and you are sending the fin, you receive the ACK, and then this is also sending the fin. Then finally you send the ACK. You say that okay, now this is the termination connection from the both side. I also wanted to terminate earlier. Now you also want to terminate. Now we are terminating connection on the mutual agreement. Okay, so this is the termination connection and final packet. This is the final packet that is going from either of side, right? Final packet from either of side. So in this case, I will say if this is the final packet, then I will just set a timer that is called time wait timer, which says that okay, I will just wait. Okay, I will not close the connection directly. I will just wait for some time. Why? Because maybe some packet is delayed and that wants to communicate with me or something, right? So it is just saying that I will just wait for some time. That is called time wait timer. The time wait timer is generally equal to 2 into MSL. What is MSL? Maximum segment lifetime, which means that a segment can alive in the network for maximum of let's suppose 2 minutes. Then I will set it to 4 minutes, which means that why I'm setting it, let's just understand. See, you are sending that okay, this is the final packet from any of the side, right? Then you will start the time wait timer. You will not immediately release your resources. You will start the timer. Why? Maybe some packet still wants to come. Okay, maybe some packet has been delayed and want to come to me. That's why you are starting the timer. Now the thing is that this packet can survive in the network for MSL only. So which means if the packet is delayed, it should be coming within the MSL time, right? Still, just being a bit more conservative, I am just setting it to 2 MSL. Okay, there is no reason why I am doing it 2. It is just a conservative behavior. Okay, just for the conservation I am saying it is 2 MSL, right? I am saying let me wait for the 2 MSL. If the packet should be arriving actually within the MSL, but still I am saying okay, let me just wait for the 2 MSL. If the packet does not arrive, any packet does not arrive, then it means that every packet has been lost, has been destroyed in the transit, or I mean I do not have any other expectation from the receiver to send anything basically. Okay, so everything if at all there is any packet in the air, in the transit, that must have been destroyed, or there is no packet at all, right? So I can now happily release the resources, so I can close now. That is called time wait timer. Okay, which is equal to generally 2 MSL. There is no rule why it is 2 MSL. There is no reason. Okay, but it is for all the implementation, for most of the implementation it is twice of that. Why it is twice? Because I'm just being conservative, that's all. Maybe it might be written here, this why it is twice. Okay, this MSL also we need to choose. There is no way to to calculate the MSL. The implementation need to choose a value for the MSL. Common values are 30 seconds, 1 minute or 2 minutes. 2 MSL is timer they use for the TCP perform an active close and send the final ACK. The connection must stay open for 2 MSL amount of time to allow the TCP to TCP to resend the final ACK in case of ACK is lost. Yeah, okay. So basically, see here in the diagram. So what I'm doing, whenever I'm sending ACK, suppose this ACK is lost, right? If this ACK is lost, yeah. So basically, maybe this 2 is because of this reason. This let's suppose this is sending in MSL time. Okay. Let me just think why they have, I think. Okay, sorry. I think there is no reason for this 2 MSL. So they are sending the ACK and then they are just waiting for some time, which happens to be 2 MSL. And according to me, there is no particular reason. We are just being conservative. It should be if you even if you do MSL, it should be fine. But just because of the conservative behavior, I am saying it is 2 MSL. Yeah, sorry, this is the same diagram. Now, see, this is a state. This is also called a state diagram. And generally, we do not need to remember for gate, and for like most of the things are either intuitive or maybe analytical. But sometimes they also ask something that has to be remembered. So basically, this is a state diagram, and we need to actually remember this state diagram. If you want to solve one or two questions, so there has been one question that is just based on the state diagram. They are saying that okay, which state it will go after sending which packet. So after sending fin packet, so they are asking, I think, after sending fin packet, which state you will go, fin weight 1, fin weight 2, time weight, like that. So they've asked based on this, or maybe I think this ACK, after sending this ACK, you are basically in the close weight. So they've asked based on this. Generally, they do not ask, but if they have asked, then you need to know this, right? Now, as I told you that we are going to come back to the retransmission timer once again, because we need to know how to calculate this retransmission timer, right? So there are a couple of timers, and yeah, last one is ACK timer. It is used if you are using the cumulative ACK, which is actually used in almost all the implementation. It says that after certain time send ACK, and which is the ACK timer. Now let's just talk about this retransmission timer once again. Let me know if there is any doubt till this point. Okay. So how to set this TCP timeout value? Basically, if you are sending something, how to determine that after how much time you should be waiting, and then after how much time you should be sending this packet again. If you keep it too short, then it is premature timeout, unnecessarily retransmission. Which means if it is keep it too short, then you are sending again and again. It is not a good idea, right? Maybe the ACK is about to come and you are sending it too short. If it is too long, then very slow reaction to the segmentation loss, right? If you keep on waiting forever and after that you send it, then it is very slow reaction to the segment loss. So it should be at least longer than RTT, because at least it takes the RTT to come the ACK. So at least longer than the RTT. But the problem here is that RTT itself varies. Why? Because you are in the congestion. You are not dealing with the hope to hope delivery. You are sending something, and because of this congestion, there is an internet in between, right? This internet or the network, huge network in between, and this another host. So basically, in the TCP, the RTT varies too much, right? This is host A, this is host B. This is not a data link layer where the RTT is fixed. I mean, you are doing just hope to hope delivery. So since here RTT also varies, so that's why what we need to do, we need to just estimate the RTT for every transmission, and then for every estimate we will be setting the transmission timeout. So what is the idea here? We will be estimating the RTT. We will be saying that okay, this time let's suppose RTT is something. Let's suppose RTT is 5 millisecond. This is my estimate. Okay, this is what I estimated. I will estimate using some technique. I will tell you how. Let's suppose I'm estimating it at 5 millisecond. Then I will say okay, if it is 5 millisecond, which means the ACK must be coming in within the 5 millisecond. Okay, but still I'm setting the timeout to be some conservative value, which is basically 2 RTT generally. Okay, I will say that if it is not coming within the 10 millisecond, although it should have been come within the 5 millisecond only, I mean in 5 millisecond only, but suppose it is not coming even in the 10 millisecond, then it must have been lost. This is my assumption, because I'm estimating this RTT. Nobody knows the RTT before sending it. You don't know whenever you are sending a packet, you don't know in how much time ACK will come. You can just estimate it based on the past behavior. Okay, let's see how to do it based on the past behavior. So what we will be doing, we will be basically estimating the RTT using the exponential average, or it is also called moving average. This is the same thing that we have studied in the shortest job first, right? In operating system also we studied same formula. There I told you that why this formula makes sense. So basically, why this formula is making sense? Because it is giving more weightage to the recent estimation, and less weightage to the, I mean it depends on the obviously alpha value, but the less weightage to the previous estimations. How it is doing? I mean let me just show you that how it is doing. So basically this is the formula that we are going to do. This is my estimate, okay, my current estimate, these are my estimate, and in the last iteration what was my estimate and what actually happened. See, I do not know what's going to happen in the future, but till now whatever has been RTT, this I know, this actual RTT I know, actual RTT, right? This is the RTT that I know, but I do not know what is the next RTT or RTT that I'm going to estimate. So this is the next RTT which we are going to estimate, but we know what have been the actual RTT before it, right? This is the real. This is also called sample RTT. Sample means, I mean, you have actually taken a sample from your data, okay, which is real thing. You know the real RTT, but last time the real RTT was this, okay. Last time means it's not 1 year ago, it's just a few milliseconds ago or microseconds ago. I mean, the last packet you sent at that time the actual RTT was this. Now you are going to estimate what should be the next RTT. That's our idea, okay. So let's just see that how to estimate it. Now what you are going to do, you are going to say that this next RTT will depend on the what you earlier estimated and also depend on what was the real thing. So for example, okay, let me just take the example here. Suppose, so initially they will give you what was the actual RTT. I mean, you do not know the actual RTT, they will give you the actual RTT, right? Okay. So let's suppose that to start with, initially actual RTT, which is ARTT, let's suppose that is given to be 10 millisecond or something, right? Now you will say that, okay, I know that previously what has happened, that actually it came in 10 millisecond. And now what you will do, you need to know that how you are going to, I mean, you need to estimate the RTT for this, right? You need to estimate the RTT for this. How you will be doing it? Since you do not know anything else, you just know that previously you came with the 10 millisecond. So you just estimate it to be 10 millisecond for now, okay, just for one iteration. So I think I have written here also for the first measurement. After the first measurement, you set it to be the initial RTT only, okay, whatever you got. Basically this is the previous measurement, I mean this is the actual RTT, but now you want to estimate. Since you do not know anything, you will say that, okay, now here the RTT is 10 millisecond only. So basically what is happening here, that you sampled one RTT, you know that actual RTT is 10 millisecond. Now what you need to do, you will say that since you do not know anything else, so you will set the RTT, that is your estimate, okay, that is also 10 millisecond. Now the actual RTT will differ, right? Now actual RTT could be anything, but now let's suppose this time the packet is coming in 15 millisecond, which means the actual RTT here is 15 millisecond. Actually they will tell you very clearly that what is the RTT that you should be assuming, I mean what is the actual RTT, and initially what should be your estimate, they will tell you very clearly. Here I am telling you that this is even before you start your experiment, I mean this is the sample that you have. Now this is your first RTT, right? First estimate is same as what you earlier had. Now this happened to be actual RTT. Now I am asking you to estimate again. So if you want to estimate again, you will say, let's suppose alpha is 1 by 2, then you will say that whatever your first RTT, I mean you will say alpha into RTT of n plus 1 minus alpha into sample RTT or actual RTT, whatever you want, actual RTT, ARTT. So you will say this is 1 by 2 into RTT, previous RTT, right? Previous what you estimated is 10 plus 1 by 2 into previous what was the actual RTT, 10. So it is basically 10 plus 10 by 2, which is just 10, right? Now you are, sorry, this is actual RTT is 15. Actual RTT is 15. Now you will say this is 10 plus 15 by 2, which is 25 by 2, which is basically 12.5. Now which means you are saying that this time my estimate is, estimate is 12.5. Now it will depend on the actual RTT that how you are going to estimate next. Let's suppose you estimated 12.5, but the actual RTT happens to be, this should be given, okay. Actual RTT, the sample always has to be always given. So these are the samples, you cannot calculate it. This is the real data. That is, let's suppose happens to be 20 millisecond. Then you will say, oh, I estimated earlier, which means earlier I estimated 12.5 millisecond, but earlier the actual RTT happened to be what was the number, 20 millisecond, then you will say, okay, my next RTT will be the weighted average of this. So alpha is 1 by 2, which means you will take just divide by 2, right? Which is basically 32.5 divided by 2, which is 16.1. You will say this is my new RTT now. Now what you will say, this time I'm estimating, which is 16.125. This is my estimate, okay, my estimate, but the actual RTT could be different. The actual RTT, let's suppose, is happen to be 10 millisecond only, actual RTT. Now I will say, okay, I estimated this, whatever I estimated, and into 1 by 2, because alpha is 1 by 2, into 1 by 2, plus whatever reality happened into 1 minus alpha, which is also 1 by 2. This is my new RTT. That's simply you keep on calculating, right? So that's how you calculate the new RTT. Now, like this very simple formula, that's called moving average. We have seen the same formula and how it actually give a importance to the new and new actual RTTs basically, right? I mean the old samples do not have any weightage. Let me just maybe just show you. See, if you just open this recurrence, then you will get to know. We have shown in the operating system already, but let me just do it clear. So if you just open this recurrence, which means you put the value of RTT n, then it will be, let me just write the RTT n. So RTT n will be this one, right? So now you substitute the value of RTT n, which means you will be getting RTT n plus 1 alpha into this thing plus 1 minus alpha into actual RTT. So if you put this thing, then it will be alpha RTT n minus 1 plus 1 minus alpha actual RTT n minus 1. So basically you are having alpha square, alpha into 1 minus alpha, these kind of terms here. So if you keep on unrolling, then it will be alpha cube and these things. So finally it will be 1 minus alpha into actual RTT of n plus 1 minus alpha into 1 minus alpha, alpha into 1 minus alpha into actual RTT of n minus 1. Similarly plus alpha, if you just keep on doing it, then alpha into I think 1 minus alpha square something, right? Alpha into 1 minus alpha square into actual RTT n minus 1. So if you keep on doing it, so if you n minus 2, if you notice, then you are giving more importance, which means 1 minus alpha importance, and then since it is less than 1, so if you multiply it will be even lesser, right? So you are giving more importance to the new samples. So I'm not giving importance to the previous sample, whatever latest happened, I'm giving the more importance to that. That is called moving average. Okay, so that's how we calculate. Now there are few things. One is called Jacobson or some modification, or then Karn modification. I do not remember the names anyway because these are not important. So there are few other scientists, those have come up with some idea of variation and deviation. Okay, variation and standard deviation, and based on that they actually said like you can actually make it better. So they have came up with some other idea of estimating the RTT, and then they have not stopped at this point. Then there was some other scientists, they have actually made it to some other formula. So basically there are 3-4 modifications, and you do not need to know that for GATE. One thing that I have observed, that most of the student just calculate these, just remember these formula, calculate the answers using this formula. But why do you know, why do you need to remember this? Because GATE is not going to ask you all the variations. There are, let's suppose, 4 variations. Okay, you should not be remembering those 4 variations. I don't see any point here. So that's why I'm not telling it. I'm just telling you that how does the moving average work. Yeah, on top of it, there are 4-5 different variations. You do not need to remember it. So that's why that's just a time waste. Okay. Now as a last topic, we are just finished with the TCP. With the last topic we are remaining, which is TCP leaky bucket and token bucket. Now if you go to the GoClasses YouTube channel and just search for the TCP token bucket GoClasses. Okay, maybe you can search like this, TCP token bucket on the YouTube. Just search like this, token bucket GoClasses. Then there will be a 30-minute video. In that 30-minute video, I clearly explain this very nicely. This token bucket I clearly explain very nicely. So I just suggest you to watch there. I mean, I have the slides and I can re-explain all the things that I explained there, but that's not the point. And I even drive this formula and how this formula is making sense and how the token bucket is working. I explained very clearly and using the geometric progression in this video. So that's very nice video, just a 30-minute video, and you can watch that instead of repeating the same thing, because I will just repeat the same thing which is already in the video. So I will suggest you to watch that video, right? Okay. So thank you everyone. Let's meet in the next session tomorrow probably. And I think Deepak is not well. So Deepak, like from the last session, if you see, he was having a cold, so his throat is not working. Okay, so maybe I think he will not be able to take the marathon today. So we will be meeting tomorrow for the new subject, or we will be updating on the YouTube channel that what is the schedule, because Deepak is not feeling well. Okay, so I will be taking the marathons. Cool. So thank you everyone. Take care. Bye bye. Let's meet tomorrow. Bye. Let me know if you have any doubt. You can just comment it out. If you have understood everything, please just comment it out. I have told everything in the TCP, right? Whatever is required for the TCP, what is the congestion control, what is the flow control, what are the misconceptions, especially the misconceptions, what you need to know, what you don't need to know, right? Do not remember any implementation. Just remember that on the timeout, go to slow start. That's the only thing that you need to remember in the congestion control. Okay, just comment it out if you have understood everything. Let me know if there is an issue or